Hello. Hello. येतोय? Okay. Uh, Very good morning, everyone. Hello. Hello. येतोय? Okay. Uh, Very good morning to everyone. I hope everyone is inside. On behalf of ISNT Pune chapter, Indian Society for NTT, and the Program Formulation and Management Board of ISNT, I welcome you all to the second day of this workshop. I request our chairman, Shri Uday Kale, to escort Mr. Mahadev Shenkar and Menka Madam on the stage for the inaugural. I request the chairman of ISNT Pune chapter, Shri Uday Kale, to welcome the chief guest of the day, uh, Mr. Mahadev Shenkar, with a bouquet. And also Menaka Madam from PFMB. Okay. Now I, now I request the chairman to give the overview of today's workshop.
Again, good morning, all of you, and very sorry for continuing the same technical problem from yesterday. So there was a technical problem today also. So it's okay, it happens. So I welcome you all to the second day, which is meant for infrared testing. You have many applications of infrared, and no doubt you will be hearing all the theory part and the practical part when we go across. So basically, again, for new people who have joined today, I would like to say that Indian Society for Non-Destructive Testing is a technical society meant for promoting entity science. There are basically four wings of ISNT. It starts with first NCB, National Certification Board, which gives certification for level 1, level 2, level 3. And now they are going to give international certification in NTT also, ICN. Luckily, we have our AGM today. So in the evening, if you would like to know something about ICN certification, I would request you to stop here and attend our that particular meet, which is just after our AGM. Then we have, what is called as PFMB, through which this program is being conducted. So PFMB is Program Formulation Management Board, which helps us, all the chapters, to conduct programs on advanced entities and other than normal, entity methods. Okay. Then we have TMB, Training Management Board, which takes care of accrediting training institutes. So we call them as ATCs. So most probably ISNT Pune chapter will also get accredited for IS 13805 and ICN both as well. Then you have basically our quarterly journal, which is published in physical form as well as electronic form as well. We have total 19 chapters spread all over the country, and we are aiming to go beyond India also. So we have formed a committee for that, and for that our National Governing Council is working on that as well. We also have promotion of student chapters in the engineering colleges. As you know, students are foundations, so we would like to build some student chapters as well, which is our main motto also for ISNT. So I think that's all, because we are already late. So I would request Kalesh to continue, and thank you very much. Once again, welcome all.
Now, a brief introduction of today's chief guest, Mr. Mahadev Shenkar. ISNT Pune chapter is indeed privileged to have Shri Mahadev Shenkar as the chief guest for today's function. Shri Mahadev Shenkar, after completing his engineering education, began his professional journey as a quality engineer in Valchandnagar Industries Limited. Due to his hard work and dedication, he was awarded the Best Employee Award many times. He later joined Thermax in the Quality Assurance Department and worked in the NDT division and continued his streak for outstanding performance. After gaining substantial professional experience, in 1990 he started his own entrepreneurial venture, Sonal Industry Services, a NDT service provider company. As his company continued to provide exceptional NDT services, in 2005 he set up his own manufacturing venture, Saksham Industries, and his plant manufactures wide range of pressure vessels, heat exchangers and tanks, and has approvals from IBR, ASND, ASME under UNB and R stamp. He is past chairman of ISNT Pune chapter and the member of the National Governing Council of ISNT. Beyond industry, he is an active Rotarian and was a 7-star president last year. He is also pursuing his passion in horticulture. I request Mr. Mahadev Shenkar to guide us. Thank you.
Good morning. Thank you, Kalash. ISNT Pune chapter chairman, Shri Uday Kale, Menaka madam, and all the participant members. खरं म्हणजे इंट्रोडक्शन कलसनी जी दिली तर आजचा जो आहे बेटर क्वालिटी थ्रू लाईफ NDT, खरं वालचंदनगरमध्ये जे म्हणजे थोडंसं मी मराठी बोललं चालेल? मराठी हिंदी ठीक. तर वालचंदनगरमध्ये म्हणजे तुम्ही आता जी ट्रेनिंग घेता 2 डे वर्कशॉप ऑन ED करंट अँड थर्मल इन्फ्रारेड. ED करंट तर हा जुनाच टॉपिक आहे, पण आजचा जो आहे तो नवीन टॉपिक तसा आहे. म्हणजे मला तर खरं त्याच्याबद्दल काही जास्त सांगता येणार नाहीये, पण ट्रेनिंग जे आपण जी घेतोय, कारण आजचा विषय ट्रेनिंग बद्दल आहे. मी ट्रेनिंग बद्दल थोडंसं मी वालचंदनगरमध्ये केलं आणि वालचंदनगरमध्ये इंडस्ट्रीमध्ये काम करत असताना दिवसभर काम करायचं आणि सेकंड शिफ्टला बाय हँड हाताने प्रॅक्टिकल तुमचा जो वर्कशॉप जो म्हणतो आपण त्याला, की प्रॅक्टिकल एक्सपिरियन्स हा खूप महत्त्वाचा आहे. त्या ठिकाणी मी RT, UT, PT, MT सर्व बाय हँड केलं आणि त्याच्याच थ्रू जो आता जो बेटर क्वालिटी आपला ISNTचा जो लोगो आहे, बेटर क्वालिटी थ्रू लाईफ NDT, कारण त्याच्या एक्सपिरियन्समुळे मी जे हाताने काम केलं आणि जे काम करत गेलो, पण आत्ता सांगितल्याप्रमाणे हार्ड वर्क आणि मेहनत हे जर आपण तुम्ही केलं तर मला वाटते तुम्ही सक्सेस व्हाल, त्याच्याबद्दल अजिबात शंका नाही. पण ट्रेनिंग हा एक आज घेतलं संपलं असं नाही. मी जवळजवळ तुमच्या माहितीसाठी सांगतो, मी IRG कोर्स 1984ला केला होता. IRG जो BRCचा जो कोर्स आहे त्यावेळेला IRG 1 तेव्हापासून मी प्रत्येक वेळा प्रत्येक सेमिनार आय हॅव अटेंडेड ऑल द सेमिनार. चॅप्टरच्या ज्या काही ॲक्टिव्हिटी असतील कुठलाही सेमिनार माझा मिस केलेला नाही. मी प्रत्येक वेळा ट्रेनिंग वेल्डिंग असतील, कुठलेही असो आपल्या इंडियाला जे रिलेटेड आहे ते प्रोडक्शनचे सुद्धा मी काही वर्कशॉप म्हणजे अटेंड करतो. मी अजूनही शिकतो. मी आतापर्यंत जरी असेल तर मी अजून शिकत असतो. नवीन काय मला शिकता येईल, नवीन काय असेल ते बघतो मी. त्यामुळे तुम्हाला जे हे ट्रेनिंग मिळतंय खरंच तुम्ही त्याचा खूप फायदा करून घ्या. हे काम करत असताना डिफिकल्टी येतात. मी आता त्याच्यानंतर मी थोडं रोटेरियन बद्दल बोलतो. मी ISNTचं जेव्हा मी चेअरमन होतो, मला वाटतं काळेसाहेब 15, 16, 16, 17 2 वर्षे आय वॉज इन चेअरमन इन पुणे चॅप्टर. त्यावेळा उदय काळे वॉज सेक्रेटरी. त्यांच्या मदतीने त्यावेळा आम्ही एवढं काम केलं की बेस्ट चॅप्टर अवॉर्ड आम्हाला इस्रोचे अध्यक्ष के सिवन आय थिंक त्यांच्या हस्ते आम्हाला बेस्ट चॅप्टर अवॉर्ड मिळाला. 2 वर्षे मी त्यावेळेला काम केलं. त्याच्यापासून माझा ISNTचा संबंध आहे. हे करता करता बेटर क्वालिटी ऑफ लाईफ थ्रू NDT मुळे आज मी या ठिकाणी उभं राहिलो. त्याच्यानंतर मी फॅक्टरी चालू करू शकलो, मॅन्युफॅक्चरिंग करू शकतो, हीट एक्सचेंजर, प्रेशर वेसल, ASME स्टॅम्प वगैरे त्यांनी सांगितलेलं त्या ॲक्टिव्हिटीमध्ये काम करत असतो आहे. आणि हे मला सगळं शक्य कशामुळे झालंय तर थ्रू EDDY. आणि EDDY म्हणजे कसं की सुरुवातीला एक्सपिरियन्स म्हणजे तुम्हाला असेल, जास्त त्यावेळेला खर्च लागत नव्हता आमच्या टायमाला. म्हणजे आत्ता इक्विपमेंट खूप आल्यात, इक्विपमेंटचा जास्त खर्च आहे. पण त्याच्यातून तुम्ही जर गेला तर तुमचं लाईफ निश्चितच चांगलं होऊ शकतंय. कारण मला हा प्रॅक्टिकल एक्सपिरियन्स आहे माझा. मी काम केलेलं आहे. त्याच्यानंतर करता करता आता मी रोटरियन म्हणून काम करतोय. गेल्या वर्षी मी प्रेसिडेंट होतो. आता हा पार्ट वेगळा आहे, पण थ्रू NDT की हा थोडं समाजासाठी सुद्धा आपल्याला काहीतरी करणं गरजेचं असतं. आपण आपलं शिक्षण घेतलं, आपण लोकांना शिकवलं, त्याच्यानंतर समाजासाठी सुद्धा आपल्याला काय देणं गरजेचं असतं. मी गेल्या वर्षभर केलं. टोटल 142 क्लबमध्ये मी जुलैपासून आमचं वर्ष चालू होतं. एक कम्प्लीट नंबर 1 मध्ये प्रेसिडेंट म्हणून काम केलं. 7 स्टार प्रेसिडेंट म्हणून मी काम केलं. आणि ह्याच्यातले 2च प्रोजेक्ट सांगतो की शेवटी थ्रू जे आपण म्हणतो NDT त्या थ्रू लाईव्ह जे करतात. तर मी आपल्या इथे जर पुण्यातले कोणी लोक असतील, एक कुंडमाळा म्हणून इथं आहे की एक ब्रिज कोसळला आणि त्या ब्रिज कोसळला तर त्याला तो कोसळण्याच्या अगोदर मी साधारण ऑगस्टमध्ये त्या ब्रिजला एक जाळी 5 mm डायमीटरची जाळी बसवली होती, मेश कम्प्लीट याला. त्याच्यामध्ये जवळजवळ लोक फोटो सेशनला जातात. 200 लोक वाचली गेल्या, म्हणजे जो ऍक्सिडेंट झाला इथला 200 लोक वाचली म्हणजे त्यामध्ये. हा सगळा फायदा NDT मुळे झाला. असे बरेचसे मी प्रोग्राम म्हणजे बेसिक आमचा सुद्धा म्हणजे आता मी रोटरीमध्ये काम करतो तो तोच बेसिक एज्युकेशन अँड लिटरसी. कारण यूथ आर द फ्युचर लीडर. तुम्ही आता काही जे यूथ आपले आहेत फ्युचर लीडर ऑफ NDT, म्हणून आम्ही यूथसाठी खूप काम केलं. मी शाळेतल्या मुलांसाठी स्मार्ट TV असतील, कारण आपल्याला फोकस त्याच्यावर होता. मी त्याच्यावर फोकस करतो की ही पिढी जी पुढची जी येतील ती यूथमध्ये येणार आहे. तर आपला या NDTचा सुद्धा फायदा यूथसाठी मुलांसाठी होईल असं आपल्या सगळ्यांनी. आता तुम्ही आत्ता नवीन आहात, काही जी लोक जुनी असतील, पण याचा फायदा यूथला सुद्धा झाला पाहिजे आणि त्यांचं लाईफ त्याच्यातून सुधारलं पाहिजे. आता आज म्हणजे एक सांगायची गोष्ट की आज जो मराठवाडा किंवा ह्या साईडला जो विदर्भमध्ये जो झाला पाऊस हे झाला, आजच्याला मला खरं तिकडे जाणं होतं. जवळजवळ 50 लाखाचं आम्ही आज त्या ठिकाणी आज आमचे दुसरे लोक पाठवली. मी इकडे मला काळेसाहेबांनी मला बोलवलं म्हणून मी इकडे आलो. 50 लाखाचा आज मदत आमच्या क्लबमध्ये मी करतोय तिथे. तर शेवटी काय की हा मी जे मदत करतोय हे कुणामुळं, तर थ्रू NDT. मी NDT मधनच माणूस आहे. तसं तुम्ही सुद्धा प्रयत्न करा. खूप म्हणजे ट्रेनिंग घ्या. आज ट्रेनिंग संपला असेतलं नाही, परत उद्या दुसऱ्यातलं ट्रेनिंग घ्या. डिफरंट टाइप्स ऑफ ट्रेनिंग घ्या. त्याचा तुम्हाला निश्चित फायदा होईल. आणि मला असं वाटतंय की आता बराच वेळ झालेला आहे आणि काळेसाहेबांनी मला खरं आमचे चेअरमन आणि त्यावेळेस सेक्रेटरी असताना आम्हाला जसा फर्स्ट चॅप्टर मिळाला, तसंच ते चेअरमन असताना त्यांच्या कारकिर्दीत सुद्धा आमची इच्छा होती की फर्स्ट लास्ट इयरला चेन्नईला मला मिळाला. लास्ट इयरला तो त्यांना मिळाला. म्हणजे आम्ही दोघं असताना म्हणजे ते सुद्धा आता तुम्ही बघत असाल की एवढं हार्ड वर्क काम करतात. त्यांच्याही काही इन्स्टिट्यूट आहेत. त्यामुळे मी त्यांचं परत मला बोलवल्याबद्दल ISNT पुणे चॅप्टर आणि हा जो केलाय PMFB जो आहे प्रोग्राम फॉर्म्युलेशन मॅनेजमेंट बोर्ड, त्यांचेही मी आभार मानतो. तसेच आपले जे इथे जे स्पॉन्सर लोक आहेत, ज्या लोकांनी हा प्रोग्राम चांगल्या पद्धतीने होण्यासाठी मदत केली आमच्या ISNT पुणे चॅप्टरला, त्या सर्वांचं मी मनापासून त्यांचं मी धन्यवाद देतो त्यांना. आणि मला थोडंसं बोलण्याची संधी मिळाली. खरं म्हणजे हा घरचा मान मला मिळाला. म्हणजे मला बाकीचं जरी मी तिकडे 7 स्टार किंवा काय असलो, खूप लोकांचं प्रोजेक्ट केलं. जवळजवळ गेल्या वर्षी 65 लाखाचे प्रोजेक्ट मी केले. आमच्या रोटरीने गेल्या वर्षी 170 कोटीचे प्रोजेक्ट केले. 170 कोटी एका वर्षामध्ये. तर तुम्ही मला खरं काळेसाहेब बोलवलं, मान दिला, आणि बोलण्याची संधी दिली. मी तुमचं खरंच मनापासून परत मी आभार मानतो. मॅडम इथे आल्यात लाभून. तसेच आता जे काय फॅकल्टी मेंबर पुढचे जे येणार आहेत, कारण ते टेक्निकली सांगणं सगळे तुम्हाला सांगणारे मी, त्यामुळे टेक्निकली मी काय बोलत नाही. एवढं एकच सांगेल की तुम्ही जे करत जा, ट्रेनिंग घेत जा, कंटिन्युअस ट्रेनिंग घ्या, वेगवेगळ्या सब्जेक्टमध्ये घ्या. थोडं सोशलसाठी थोडासा तुमचा फुलना फुलाची पाकळी तुम्ही आपलं करता करता दुसऱ्याचं करा. त्याच्यातला खरा आनंद आहे तो सगळ्यात महत्त्वाचा आहे. थँक्यू मला इथं बोलावल्याबद्दल. थँक्यू उदय.
Thank you very much, Shankar sir. You have been always supportive to the ISNT activities in all its endeavors. So, as a token of gratitude, I request our chairman to felicitate Shri Shankar sir. Now, I request Mrs. Menka Madam from the Program Formulation and Management Board of ISNT to guide us today on the workshop. Yeah, thank you.
Respected dignitaries on the dais, off the dais, respected faculty members, dear participants, good morning to all. As you all would be knowing, infrared thermography is one of the advanced NDT technique, a non-invasive NDT technique which finds its application starting from medical to military, intelligent welding to material characterization. So it's really an honor and privilege for me to be a part of this two-day workshop, particularly today, which deals about thermal infrared testing and its applications. First, I would like to place my sincere gratitude to ISNT Pune chapter and PFMB for giving me this opportunity to be a part of this two-day workshop. Coming to the outline of this workshop, how we designed it, we actually thought that this workshop should be providing you a basic idea or a knowledge transfer on the basics of infrared testing and some of its application. We may not be able to cover the full-fledged, but we are planning to try to cover starting from the basic to its application and of course the demonstration part as well. The first presentation would be done by Professor C. Krishnamurthy sir from IIT Chennai. He has immense experience on this field and he would be covering on the basics of infrared thermography, giving you an overview and heat transfer phenomena as well. And the next topic would be covering completely about the equipment which you are using. If I'm planning to do an application on infrared testing, then what kind of camera should I select? What are the parameters I should look for? Those things will be covered by Dr. Sharath from Indira Gandhi Center for Atomic Research, Kalpakkam. Of course, the third presentation would be delivered by Professor Ravi Babu sir, IIT Delhi, and he would be covering the most important part, the recent advances in thermal non-destructive evaluation and the how to use active thermography for evaluation of materials. So, and the last two topics would be covering the applications of thermography both in the, as a condition monitoring tool and as material characterization and material evaluation. So this is the idea with which we have designed this course. I hope this would be of immense use will be fruitful for you all. With that, I would like to thank the ISNT Pune chapter for the opportunity.
I now request our promotion partners, One Stop Entity, to briefly introduce themselves.
Thank you and good morning to everyone. Kindly excuse me for my low voice today. I'm a little unwell, but very happy to be amongst all of you since yesterday. And I see many of the new faces attending this today's workshop. So it's an honor for me to present One Stop NDT to you and help you understand how our platform can help you in your NDT journey. So One Stop NDT, we are a global NDT community. What does that mean now? So when we say it's a global platform, it's a community platform, the basic try and the basic idea is to bring each and everything related to NDT on a single platform. So basically, the purpose of One Stop NDT is to inspire innovation, collaboration, and awareness in the NDT industry by bringing together all the possible available resources across globe. And be it you are coming from any background and any user persona you are, whether you are a student, you are a professional, you are a job seeker, you are an equipment manufacturer, service provider, you are a training institute, CXO, anybody, but you are relevant to NDT and its applications, I'm sure you will get information related to whatever you are searching on our platform. We have a beautiful modern UI UX driven website along with the very strong digital presence using all the social media handles, YouTube, LinkedIn, newsletters, and our monthly magazine as well. On our website, you will get to explore a lot of resources. So we have 1,000+ global entity companies where you can find out different equipment manufacturers, service providers, training institute, associations like ISNT, and so many other companies as well. We have a content, very rich content available with more than 800+ articles on a different topics submitted by the experts, researchers, student, and the professionals. Along with that, we have upcoming events, webinars happening in the industry across the globe. If you're searching for any kind of jobs related to NDT in any region of the world, you can definitely get the latest hiring job post on our website. Along with that, we have few interesting initiatives as well. Where we are actually engaging users and trying to educate them. So we have NDT Talks, a monthly panel discussion where we are inviting experts and a moderator to discuss on the trending topics in the industry. We have NDT Trends, which is our monthly magazine, and we try to bring whatever are the latest happenings in the previous month of time to our users and to the community members. So with all these resources and the popular initiatives, we are trying to educate the community. We are trying to bring the community together and help each and every individual who is a part of this very niche industry, but it's very important, as even our chief guest mentioned, how crucial it is in terms of safety and the quality assurance of everyone's life. So this is what One Stop NDT is all about. You do check out our website, follow us on LinkedIn, and you can subscribe to our newsletters as well, so that you can stay up to date with the latest happenings in the NDT industry. We are also here for today, and will be happy to interact with every one of you. We have a beautiful magazines to show you as well. And lastly, thank you so much to ISNT Pune chapter, Uday sir and his team, for giving this opportunity for us to promote this event, and looking forward to interacting with all of you. Thank you so much.
Okay, now we are coming towards the end of our inaugural program. So myself, Kalesh Nerurkar, the Honorary Secretary of ISNT Pune chapter, would like to propose the vote of thanks. First of all, I would like to thank our chief guest, Mr. Mahadev Shenkar, for gracing the occasion today and guiding us, and also the PFMB board member, Menaka Madam, for guiding us today and giving the brief overview of the program today. I would like all the supporting technical staff who are making this program successful with their technical expertise, and all the delegates who have attended the program today. Thank you. So today we will start our next session immediately after this program. Thank you.
Good morning. Yeah, I'm not able to hear you fully. Your volume is low. How is my volume? Is it okay? Okay.
Yeah. Are you able to hear me now, sir? Okay. So I will introduce Professor C.V. Krishnamurthy. He did his MSc Physics from IIT Mumbai. He obtained his PhD from IIT Madras in 1989 in condensed matter physics. Between 89 to 90, he worked as a lecturer in Department of Physics, Regional College of Education, Mysore. He was CSIR fellow between 1990 to 1993, working on non-nuclear optics at the Department of Physics. Between 1993 to 2002, he worked as staff scientist at Helios, a private R&D company, on projects related to electromagnetic wave propagation for the DRDO and Indian Navy. Between 2002 and 2010, he was affiliated to the Center of Non-Destructive Evaluation Department of Mechanical Engineering at IIT Madras. He was with Department of Physics IIT Madras since 2010. He retired from the Department of Physics in June 2025 as full professor. Currently, he is teaching at the Department of Medical Sciences and Technology IIT Madras. His research interests involved the development of diagnostics tools for non-destructive evaluation of materials and industries components using ultrasound, infrared thermography, eddy current, and microwaves. His recent interest has been in studying the peculiar structural and electrical properties of water under nano confinement. He has worked on several research and developmental projects funded by DST, DAE, BRNS, ADA, ISRO, and DRDO agencies. He has carried out consultancies for Apple, US, and Saint Gobain in India. He has over 120 technical publications and has presented papers at several national and international conferences in India and abroad. He shares 4 Indian patents and a US patent. He is co-recipient of prestigious DRDO Academy Excellence Award. He is one of the co-founders of startup community ABRTTI that is developing sensors to detect buried objects using electromagnetic waves. He regularly gives lectures and demonstrations in schools and colleges for both students and teachers as a part of outreach activity. He is Life Fellow of Indian Society for Non-Destructive Testing and Indian Association of Physics Teachers, IAPT. So over to you, sir. The stage is yours.
Oh. Can you tell me how much time I have for the presentation?
Sir, one hour.
1 hour. Okay, fine. Thank you. So I'll share my PPT. Can you see the slide? Okay. So shall I start now? Okay. Good morning, everybody. Thank you for giving me an opportunity to share some of the basic ideas involving infrared thermography. I thank the organizers once again. I thank Mr. Uday who has introduced me. So let me uh, begin. So when we start talking about infrared thermography, the first thing that we need to keep in mind is the following, that all objects, whether they are in the gaseous state or liquid state or solid state, as long as they are at finite temperatures, I mean absolute temperatures, T is in Kelvin, and in absolute temperatures, at the finite temperatures, they radiate heat. And what you see on the left is a photograph of a person taken using visible region of the electromagnetic spectrum. And what you see on the right is an image of the same person taken using some wavelengths in the infrared region. So there is a big difference between the two images, and there is correspondingly there are different kinds of information that one can obtain from the images. What you see on the right hand side, which is the infrared image, it is taken by an infrared camera. It is the color scheme used in this image is false colors. They are not true colors simply because we don't see infrared. Our eye cannot see infrared radiation. Our eye can see only up to the red. From violet to red is the range that is what we can see by eye. Beyond that, our eye cannot see. So what the camera does is captures that information and presents it with a artificial coloring, or the colors are chosen by the user. So you choose the color scheme you want to render the image. But what you see, what is important is the contrast. So when you choose whatever color scheme you have, what you will be looking for is the contrast between different parts of the object, and seeing whether these different portions of the object convey information, what kind of information can be obtained by looking at various portions of the image. That is what is the information content that can be obtained from the infrared image. So it's important for you to keep in mind that the images obtained from an infrared camera, you will be seeing many of them in the workshop today. They are all false color images. But what is important is that the contrast, what we are looking for is the contrast, and how is this contrast helping us understand different things about the materials. So when we say that the materials which are at finite temperatures radiate heat, and the way it radiates, the form of this radiation of this energy is via electromagnetic waves. So electromagnetic waves comprises of all the way from X-rays down to radio waves, the entire spectrum. In that, a small portion is the visible range, and another small portion is the infrared range. And so if you have a camera which can be sensitive to the infrared part, it will be in a position to give an image in that using the information in that region and present it to us. So it's a radiation, the energy is getting radiated, and which means that I can stay at a distance from the object without touching the object. I can collect that radiation and get the information about the object. So that is what is primarily the advantage of using this infrared thermography as a diagnostic tool. So if you were to ask what is exactly this IR thermography, the first part is this, that we collect radiation, this whatever is the radiation emitted by the object, we collect that radiation within this infrared range of wavelengths or frequencies of the electromagnetic spectrum. That's one part. And then we use that collected radiation and try to quantify. What are we looking for? We are trying to quantify it and see if we can estimate the temperature of the object that from where this radiation has been collected. Either the object or a portion of the object from where the radiation has been collected, we would like to quantify in terms of the temperature. So these two parts are involved when we say we are dealing with infrared thermography. So if you are not in a position to quantify the temperature of the object, you can still have a qualitative picture. You can see, as I said, you can get some contrast between different portions of the image of the object, and you can say relatively one portion is hotter than the other portion. That even though you may not know the exact temperature, you may be in a position to say how the different parts of the object are with respect to each other. So there's a qualitative assessment that can be done, and there's a quantitative assessment. By quantitative, I mean associating a temperature with each portion of the image. Both are useful, and sometimes it is difficult to quantify in terms of temperature, but still a qualitative picture is also very useful when we are looking for features in a scenario in terms of inspecting a component or inspecting a facility. Whatever that we are looking for, it's a good diagnostic tool, as we will see as we go along. So this feature where we collect the radiation and estimate the temperature, this is called radiometry, or it's also called pyrometry. Slight differences in terminology. You can collect the radiation and estimate the temperature without giving the details of the image, in which case it is like a thermometer. Just like a regular thermometer, it will simply register a temperature, that's all. It will not tell us anything about different portions of the object. It's not an image, it's just a number, a temperature obtained by collecting radiation from the object. So objects details in terms of spatial details will not be there, but the information in terms of its object's entire temperature that is collected via the radiation, that is estimated. So that is called an infrared thermometer, which is also what you get from a handheld pyrometer. Of course, you can also have a camera where you have a collection of detectors kept in an array, in a 2D array, just like our visible cameras. There is an option to have an array of detectors which will enable an image to be captured, which are the infrared imaging cameras. So by and large, these are the two forms by which we can collect the radiation. In terms of pyrometric devices or bolometric devices, or which will give you only the temperature and not the image. The other is a camera which not only gives the image but also can give the temperature of the spatial variation of temperature over the image. Now, when we collect radiation, the radiation that is coming into the camera. So in this picture, what you see on the right hand side is an infrared camera, and it is looking at a situation in front of it, and radiation is falling into the camera from various parts of the scene. So you can have radiation coming from the object, which is what we are interested in, the direct, which is green in color. That is what we are interested in, because we are trying to look at the object's features. But because the object is kept in ambient conditions most of the time, it may be reflecting radiation coming from somewhere else. For instance, a sun can be a source. It can reflect sunlight. The object can reflect some amount of sunlight, which will carry infrared radiation as well. All those other reflections will also get into the camera. Along with that, there is some radiation coming from the atmosphere that is between the camera and the object. Remember, I told you that because we are collecting radiation via electromagnetic waves, the detector or the camera can be very far away from the object and still get information. But the more you are further away from the object, there is a possibility for some atmospheric contributions in between the object and the camera. What we have seen in the picture is what is written as atmosphere. That will also radiate because it's at some temperature. Since everything which is at some temperature will radiate, whatever you get in the camera is a collection of all these contributions. Contribution from the object, which is at some temperature, contribution from the atmosphere, which is at some temperature, contribution from the sun maybe or some other source of heat, that is, which is at some temperature. All of those will combine into the camera. So when you try to quantify at the received with the received radiation, you will have to be careful in trying to understand what is coming from the object and what is coming from the other parts. It's a little involved, this exercise of trying to separate out the contributions that we will discuss later on. But you just have to keep in mind that when the camera is looking at a scene, just like in a regular camera, when you look at the scenario in front of you, there are many things. Apart from what you are trying to photograph, there are other objects as well. Similarly, there are other contributions here as well. So one has to keep that in mind when interpreting the data that comes out of this. So before we start discussing the quantitative aspects, we need to know what can be the ideal radiator and an ideal absorber, which will help us in quantifying what are non-ideal or real objects. How are real objects different from ideal objects? We need to make that distinction. So we would like to know what is an ideal object in terms of the heat radiation characteristics. So an ideal radiator has these properties that it will radiate. It's depending on only on its temperature. The moment the temperature is given, or if the object is at some temperature, it will radiate in a specific way. That specific way, that is a distribution of energy over a wide range of wavelengths. The radiation is coming from the object at different wavelengths, and all of this radiation is coming in a certain way based only on its temperature, no other variable. And that it follows a certain distribution which is described by what is called as a Planck law. And the shape of that distribution is given here for different objects at different temperatures. So if you look at the topmost curve, that's an object at 6000 Kelvin radiating electromagnetic radiation. And it's, as I said, the body radiates electromagnetic waves across a wide range of wavelengths or frequencies, but they are not all with the same energies. So if you ask what is the energy radiated at one wavelength, it is not necessarily the same at another wavelength. So you will see that it's a distribution. The weights are different. So you will see for 6000 Kelvin, the peak is somewhere near the visible region. And if you go to lower and lower temperatures, you will find that the maximum radiation is at some other wavelength, not at the visible region. So this is a characteristic of the distribution function, but this is also been tested experimentally. And we have nearly ideal radiators in real life that we can test and check whether this Planck distribution law is valid or not. So the other characteristic of an ideal radiator is that it absorbs all the radiation that is falling on it. It does not reflect. So its reflection coefficient is 0. It will only emit. It will absorb and emit. It will be a complete, it absorbs 100% and it radiates 100%. That is the ideal radiator, which is also an ideal absorber. So it's called a black body. The name given to such an object, it's called a black body. And though this is an ideal situation, we have real world examples of how close to this black. I will show you one example at least later on. So if you go to lower temperatures, I told you that the peak will shift. So you will notice that when you are somewhere around 2000 Kelvin or 2500 Kelvin, as you see, the peak is occurring somewhere in the wavelength of 1000 nanometers or so, not in the visible region. You can compare the two curves. So the higher temperature will make the peak shift to the higher frequencies, and lower temperature will shift it towards lower frequencies. So this is something that is a property of the object that radiates, and we have to keep this in mind when we want to understand or interpret the radiation coming from hot objects or cold objects. All these things, we'll have to keep this in mind. So sun is a very good example of a black body. So I mentioned to you that there is a real world, there are several. One of them is the sun, which is very close to a black body. So by that, what we mean is, if you look at the yellow colored portion of this curve, that is what is actually measured. And if you were to use the Planck law to fit this function, you will find the curve there. The curve is having a label which says 5250 degrees centigrade. So that's the temperature of the sun's outer portion, and which is what is radiating and which is what we are collecting from not the earth but outside the earth. We are in space and collecting the radiation. If we were in space or very far away from the earth's surface, collect the radiation, you will find that spectrum will be very close to the Planck law, and we can use that information to estimate the temperature of the sun. And this is a routine way of estimating the temperature of all the stars in the universe. Every star radiates, and every star is radiating in some spectral content, and they will all at different temperatures. And we can estimate the temperatures of the stars using this. You just collect the radiation from outer space and fit it to the Planck function and estimate the temperature. You will find that you can ascribe a temperature to this object because the function, the shape looks very close to the Planck distribution function. But if you try to measure the radiation from the sun by a camera or any detector at the surface of the earth, you will find a different distribution, which is what is shown in red, because of various gases that are present: water vapor, carbon dioxide, oxygen. They all absorb some of these radiations, and it will look very different. You will see it's all broken up, the red curve. With that information, we cannot estimate the temperature. It will be difficult. But you can see roughly the envelope is falling on that Planck curve, roughly. That's the only indication, but you cannot go into any detail. But this is just to tell us that atmosphere can absorb radiation, and depending on the amount of water vapor present, depending on the amount of carbon dioxide present, it is what you receive in the detector is not what has been emitted by the object. That is what I want you to keep in mind. It gets some of which can get absorbed by the so-called atmosphere that we were talking about earlier. So if we were to collect all that radiation, when we say that, we mean that we are integrating over the spectrum, so to say. That means I have added up all the contributions from every wavelength in that Planck law. If I do that, I get the total power, which is found to be equal to the fourth power of the temperature of the object. So this is the most important thing that we will be using in infrared thermography. We are trying to ascribe now a temperature to the object, and that temperature is coming out in this formula. So what will I do? If I have a detector which can collect radiation over the full spectrum of the infrared region and if it follows the Planckian distribution, then the total power that the detector has captured can be related to the fourth power of the temperature of the object. Now, there are some fundamental constants. One fundamental constant, which is the Stefan-Boltzmann constant written there. There are two other things which are related to the geometry of the object. One is the surface area of the object that is emitting. The other is the emissivity of the object that is emitting. So these are properties of the object that is emitting. Assuming the detector is an ideal detector, you will find that you are getting the information about the object's temperature. This also implies that if I have to say that this is the temperature, I should know the emissivity of the object, and of course I should know the area of the object. So you can use this expression to find out what is the heat transfer between two surfaces, two objects. So in the bottom part of the slide, you have two objects. So just a second. So if you look at the bottom part of the slide, you will find two objects, colored objects. One is at T1 and another is T2, and they're both radiating. And we can ask what is the power radiated by each of these objects. And we now know that the total power radiated by each of these objects will be proportional to their own temperatures, the fourth power of their temperatures. And what's the net transfer that is taking place? It will be what the expression is giving you. So this is something that we will be using to estimate the object's temperature if the detector is at some finite temperature. In the first top expression, I didn't tell you about the detector. I simply said it's an ideal detector and it was as if it was at some zero temperature. That's not possible. So we have, if a detector is at room temperature, for instance, and if I am trying to measure the radiation coming from another object, which is say at 100 degrees Celsius, and the room temperature is say at 30 degrees Celsius. Now there is a difference in temperature. Obviously, powers radiated and received are different. So what I am detecting will be over and above what the detector's inherent radiation that is coming up. You remember that the detector is also at some temperature, so it will be radiating. And that radiation also will be getting absorbed by the detector, part of it, within the optics that is present in the detector. So a portion of that will get back into the detector. So it will not be, it is not possible to avoid that. So you can call it like a dark current kind of thing. So even if I close the camera, you will find some signal coming. That is because of the internal radiation that is coming up that you cannot avoid. So, but if I open the cover of the lens, you will start seeing an image. And that is because the external radiation is coming in and over and above the internal radiation. So that over and above thing is what we are actually trying to say. We are detecting something above the room temperature or above the temperature of the detector. If the object and the detector were at the same temperature, what you will see is a uniform feature. There won't be any features. It will be simply like a blank screen. Because there is nothing to differentiate any portion of the image. Everything is at the same temperature. So there is no net transfer of heat energy taking place for me to register any change. So what I will see is a uniform screen. I will not see any feature. If the room in which I am taking the image and my detector is all at the same temperature, it's very difficult to find out what is there in the room in using the infrared image. You have to keep in mind that we are now talking about an infrared image. And we have to understand that the image contrast depends only if there is a difference in temperature. Otherwise, we are not going to see anything. So this is the idea here, that the detector is usually at some temperature and the object should be at a different temperature in order to see a difference or show some features in the image. So it also, this will tell you that if I were to cool the detector, I will get better and better resolution or better contrast, because I'm trying to reduce the difference, I increase the difference between the object or the environment and the detector. If I cool the detector, so cooled detectors are available, they are sold. Usually they are a little more expensive compared to the uncooled detector. So you will see some more people discussing about these types of detectors. But the point is that a cooled detector is always good, but a little more expensive. Okay. So the wavelengths that are specific of interest, direct relevance to infrared thermography are broadly two groups. One is the short wave length regime and another is the long wavelength regime. They are labeled as SW and LW. Roughly 3 to 5 micron wavelength regime is where the short wavelength uh, portion is there, and from 8 to 14 micron is where the long wavelength regime is there. And you will find, when you look at the cameras, the specifications of the cameras, you will find most of the cameras will fall into either one of these two categories. Of course, there are other kind of cameras which are more specific to certain wavelengths, but I'm giving you a broad classification that you will find something between 3 to 5 is one set and 8 to 14 is another set of cameras. It's based on the detectors. So the main thing that we need to keep in mind in infrared thermography is this, that it's a non-contact mode of assessing the information. You don't need to keep the sensor in contact with the object. You can keep your sensor far away. You can have, as I said, a non-imaging detector, which will simply collect the energy and give you an output proportional to the energy collected. And that is one form of detection, which could be called pyroelectric and all that. So if it is taking the photons, you can also talk in terms of that language. If you take photons and register some signals based on that, it will be a photonic or photoelectric kind of signal. And it could be photoconductive when resistance can change because of the incoming energy. So there are slightly different ways by which the sensor is responding to the incoming energy, but all of them can be non-imaging. That means I simply collect the radiation and register a change. And that change that is registered is somehow connected to the temperature. That is one way of doing it. The other is the camera based, that is image based. I can have, as I said, an array of detectors which will give me information in a spatial way, which like a regular camera, pixel based information can be obtained. So sensors can have, like, point type is the non-imaging type. Line scanning can be used to construct a two-dimensional image. A one-dimensional scan can be converted into a two-dimensional image after multiple scans. Or you can have arrays, 2D arrays, which are very similar to the visible cameras, which we are talking about as infrared cameras. And what is interesting about this way of inspection or trying to diagnose the object is that it's real-time information. Whatever the object you are looking at, whatever changes that are taking place in the object, you will be able to monitor that in real time. Whatever you see on the camera will be directly related to what is going on in the object. If the object is cooling, or if the object is heating up, or something is happening to the heat transfer characteristics, you will be able to see that in real time, which is very important and very useful for diagnostics. So we try to recall what are the possible ways by which heat can be transferred. we know that the heat can be transferred via convection, conduction, and radiation. And what we are interested is, from an infrared thermography point of view, we are interested in the radiation coming from the object that is getting collected by the detector. That is the detection part. But within the object, all the three possibilities are there. Either a set of one object or a set of objects. There is a possibility for internal processes that are taking place, which can be convective, which can be conductive. If there are two, three objects making up a system, how the heat is transferred across these objects depends on whether they are in contact or not. What kind of contact is it? Is there a fluid between them? Is there a solid contact? Depending on that, the mechanism of heat transfer will be different. So within the object or system, there can be all the three possible ways of heat transfer. But from a detection point of view, I am sitting somewhere and using the camera or a point detector to collect the radiation. That is only radiator. But can I say something about those internal processes using the information that I'm collecting sitting far away? Can I infer anything going on in the system? That's the kind of question that we would like to know. And the answer is yes. To some extent, we can say what is going on inside by trying to capture the images as a function of time. We can get some information about the internal processes that are taking place using an infrared camera, for instance. So there are three properties of materials that will keep coming up in some way or other, which will control the way the heat is transferred internally. So we have thermal conductivity, we have heat capacity, and emissivity. Now, among the three, you will find that thermal conductivity and heat capacity will be involved in the internal heat transfer between various parts of the system. And emissivity is where it actually tells us how much energy it is radiating. We were right from the beginning, we said the objects are radiating electromagnetic energy, but the amount of energy that is radiated is controlled by this parameter or property called emissivity. It's extremely important for us because from that only we get whatever we are receiving is only because of the emissivity property of the object. If the emissivity is very, very small, so emissivity is a value that ranges from 0 to 1. I will amplify that point later on, but it's a number which is between 0 to 1. 1 means it's a perfect emitter, which is like a black body. Ideal. Very few materials are like that. You can go very close to that, 0.95, 0.98. We can have materials which are very, very close to 1. And there are objects which are very poor emitters, which is very close to 0, 0.01, something like that. If you have such a poor emitter, even though internally some heat transfer is taking place, because it's very poor emitter, amount of radiation radiated by that is very low. So what you get outside is not a correct picture of what is going on inside. So that is the reason why the poorly emitting objects will not be able to convey, or we will not be able to infer information about what is going on inside if the emissivity is very low. The other two, of course, are the properties which govern the heat transfer among the various parts of the system. A combination parameter which is very useful in studying the time-dependent phenomena is the thermal diffusivity. You will find that it's related to conductivity, density, and specific heat capacity. So this will tell us how quickly the heat is moving from one place to another place within the object. So if you were to monitor an object via an infrared camera in time, in real time, if you see the object's temperature changing in time, that change is related to the thermal diffusivity of the material or parts of that material. So that is what governs how fast or how slow the process is taking place. Okay. So this is just a table of properties to tell you how different materials have different properties, basic thermal properties apart from density. And what is of interest right now is this: there are two things. One is you find that there are materials which are not having the same value in all directions. That is, the material has anisotropy. If you look at the red boxed section, we are looking at graphite material, epoxy, a thin layer, let us say. The property in the perpendicular along the thickness direction is different from the property along the in plane direction. So in plane and out of plane properties are different. So there are materials, wood is a good example of that. There are many materials which have this feature that their properties are not the same in all directions. If they are the same in all directions, we call them isotropic. If they are different in all the different directions, we call them anisotropic. So there are materials, which means the heat transfer will be different in different directions. And that is important for us when we are looking for various situations involving different kinds of materials. The other thing is about the air. Air, even though it has very low thermal conductivity, its diffusivity is very, if you look at the number 58 in the units that have been described here, it's much more than the numbers that you see. It's comparable to something like graphite, steel, somewhere near steel, the diffusivity. So that means it can rapidly transfer heat from one place to another place. Even though its thermal conductivity is poor, specific heat is okay, comparable to other materials, but thermal diffusivity is pretty good. So that is something you keep in mind, because air is going to be there in most of the situations that when we look at thermography. So how does this heat, so if I have defects in materials, which is one of the things that we will be looking at when we are trying to look for, when we are inspecting a material and we want to know whether there are any defects in the material, air voids or heterogeneous air pockets, voids, something, slags, anything like that, water ingress, some water is trapped somewhere, can I detect it? If I want to know, that means I have some material A and some material B inside A. So then I would like to know how the different heat transfer characteristics between these materials will affect the surface features, because what I'm seeing is only the surface. I do not see the inside of the object. I cannot see the inside of the object. I can only see the surface of the object. From the surface, can I tell something about the inside? This is the question that we are looking at. So if you look at this situation where there is a defect, and this defect is having a lower thermal conductivity compared to the medium in which it is placed. If it is like that, and if there is a heat flow from the top surface, you will find that the heat is flowing away from the defect and going, surrounding it and going, bypassing that defect and going, because it's like somewhat like a resistance to the flow of heat. The thermal conductivity is like some kind of a resistance. If it's high, it's good. A good path is there for heat transfer. If it's low, it's resistive to the flow of heat. So you will find that since the heat is flowing very efficiently around the object, but not through the object, you will find that on the surface, you will find a hot spot. That means if I send heat, if I, let's say, heat the surface and see how the heat is getting into the medium, I will find that heat is going in the region where the defect is, heat is going very slowly into the medium. But surrounding places, heat is going into the medium very rapidly. So that difference will mean that on the surface, I see some region which is hot or hotter than the surroundings. That is what we are seeing on the top. The scan, if you take a image, you will find a hot spot on the surface. So this is a characteristic coming from differences in the thermal properties of the internal parts and the basic medium. So you can ask what happens if it's a cold surface. So again, there's a relative change that we can see. So all these relative changes this is a case where the defect happens to have a higher thermal conductivity than the medium. So it will have a relatively a cold spot compared to the surroundings. So these are the ways by which we understand how the heat is flowing through the object and how the internal or parts of the object are to either block the flow or allow the flow to take place more efficiently. Those differences will be showing up on the surface and as contrasts. And that information is used to identify the internal features. So this is how inspection has to be interpreted. So as I mentioned, the radiation transfer that we are primarily interested in can be contaminated by other things. It can have other sources other than what we are interested in. We are interested in collecting radiation from the object, but there are other sources of radiation that may fall on it or come directly to the camera. So all these things will contribute to the received radiation, and we have to, all that cannot be ascribed to the object. So our assessment of the temperature will be wrong if we try to say the total received power is equal to the fourth power of the temperature. If you use that information, then you will be wrong. You have to see that its contributions are coming from other places. And what this Kirchhoff law tells us is that usually objects which are opaque, which means it doesn't transmit, that means the transmission is very low. So the absorptivity will be just equal to 1 minus reflectivity. Okay. So some radiation is falling on the object, a portion of it is getting reflected, a portion of it is getting absorbed, a portion of it is getting transmitted in general. But what is getting transmitted, let's say, is negligible. So you are only left with what is reflected and what is absorbed. So that is what this is saying. Usually in the infrared studies, we will be talking about materials which are having very poor transmittivity. So this is very commonly encountered: absorption and reflection. These are the two properties. So if you look at this image on the left, you see that there are some materials which are transparent to the infrared and some materials which are not. So of course, in the visible spectrum, on the top photograph is a visible photograph. You cannot make out both the glasses have the same or very little difference you can make out between the transmission characteristics of the two glasses. But in the infrared, you will see one of them is opaque. One glass is opaque. That is a normal glass. If you make a glass or use common salt, that is NaCl, you can make a glass out of that. If you make that, then it is a transparent to infrared, which is why you see that infrared radiation is going through the second on the left of that spectacle. On the right, you have normal glass, which is blocking the infrared radiation. This is very important when we are dealing with inspection of materials, different kinds of materials. So again, this is amplifying the point that we are just talking about. So there is this visible photograph of a hand kept behind the window, a glass plate, but that glass plate is blocking infrared radiation. So I don't see anything behind that. I see only the portion that is outside the glass plate. That is because of the transmission characteristics being very poor for normal glass in the infrared region. You will see that red curve at the bottom, which you will see that it's going to 0 from 4 micron onwards. So most of the infrared thermography occurs after that in the long wavelength regime and room temperature, near room temperature. So you will find that because it is a very poor transmitter, it's like opaque object. And that's the reason why we are not able to see beyond the glass. So there's another thing about what we talk about as opaque and transparent. These are all wavelength dependent. So this is to tell us that what appears in the visible region as opaque, like the black plastic, whatever he is holding on the left, it's opaque in the visible region. But it need not be opaque in the infrared region. So this is just to show you that objects which we are used to the visible spectrum and in the sense of the contrast, the color contrast that we see in the visible region is not what it is in the infrared region. Materials have different properties in the infrared region. So that is something we have to keep in mind when we are doing inspections involving different kinds of materials. The text is only trying to tell you where the difference is coming and why it is so in some sense. So when we move away from a real, ideal body to a black body, real body, we need to know what is it that we know that most of the bodies are not ideal black bodies or ideal radiators. They only have approximately approximate black body, which is called a gray body. The gray body, which is shown here as a green curve, is following the Planck law, but with a different emissivity. So the shape is somewhat similar, but the value of the emissivity will be different, that value between 0 and 1. That's the next best thing that we can think of in terms of interpreting results. So the example is MgO is one example. There are many other examples which are behaving like gray bodies. They're easy to analyze. When you look at carbon dioxide, it's a gas, it absorbs selectively. So you cannot ascribe a temperature to it in terms of the Planck law cannot be used because it's not following any shape that is described by the Planck law. So I cannot ascribe a temperature to, if I collect radiation in this way, I cannot use this information to ascribe a temperature to carbon dioxide gas. So, but I can do that for MgO. I can of course do it for carbon. C stands for carbon, graphite and things like that. So the other aspect of emissivity is to do with the surface roughness. So if the surface is very smooth, like for instance metal objects, they are all shiny. Typically a well polished metal is a very shiny object, and you will see that it reflects, it behaves like a mirror, which is on the left hand side. What is called a smooth, labeled as smooth, is that it follows Snell's law. If I shine light in one direction, reflection will be following the Snell's law. It exactly goes in the other direction. But if the surface is not smooth, it becomes increasingly rough. Then the reflection is not in one direction, but in a range of directions, which is what you see on the rightmost curve. You see it's distributed over some angles. So a regular rough surface, which is also true for infrared radiation, even though you are familiar with this for optical region, the same Snell's law is valid for infrared. It's the same electromagnetic wave. So any smooth object will be reflecting very strongly in one direction and not in other directions. So if the surface is rough, and more rough it is, the better it is to distribute that energy over large angles. So if you look at for instance, if you were to look at emissivity of materials, you see that you take aluminum, very polished aluminum, emissivity is very poor. So you cannot use this material, a polished metal, and it will be very difficult for you to estimate the temperature of an object which is highly polished because of this property. Emissivity is very low, and also direction is very limited. It can only emit in one direction and not in other directions. So as it becomes oxidized, it becomes little better. You will see aluminum oxidized, which is natural oxidation process. You will see it's improving a little bit. So it also direction wise also it gets a little better. So any dull surface, matte finish, these are all good objects or surfaces for infrared purposes. So there's another thing about this collecting radiation. If you keep the camera at different angles, you are collecting different projected areas from the object, as you can see from here. You see the object is, let's say, the blue plate, and you are holding it at different angles and collecting radiation. You see only a projected area is involved in the collection of radiation. So there is a cosine function that describes this variation. Now, if you look at the emissivity on top of this, in addition to this feature, you have emissivity of an object. You see that polished materials will have emissivity very small value, but very close, very for very in the vertical region only you see it within the 10 degrees thing. When you go to an ideal object like a black body, it radiates, or it is efficient to radiate energy in all directions equally. So you see a curve that goes all the way D. D is a black body, which is saying that it emits efficiently with equal efficiency at all angles. And you will see that opaque objects, opaque non-metallic objects, which is called opaque dielectric materials, you will see the curve C, which is having a good emissivity in up to about 40-50 degrees, or maybe even up to 60 degrees, and there it will start falling. So if you go to a side and try to view the object and try to collect radiation from that and estimate temperatures, you will be having errors. You will be better off within the 40-50 degrees of the normal, surface normal, to be able to get good information about the object. So these are the emissivities of typical materials. You will see that emissivity of lamp black, what is written is 0.96. And sometimes water is also a good black body, 0.98. It behaves like black body in the interval that we are talking about. So these are all useful pieces of information that can be used when we are doing diagnostics. So there are two modes by which we can collect, quantify the information that we collect from the object. One is called a passive thermography, the other is called the active thermography. By passive, we mean we only collect the radiation from the object. We don't do anything to the object. We simply collect the radiation and interpret that radiation. When we talk about active, we are actually stimulating the object by different methods. And when we stimulate it and then look at its response via an infrared camera, that is what is meant by active. And there are many ways by which we can activate or stimulate the material to let it radiate under short durations of a pulse, for instance. I can give a pulse of heat and look at its response. That becomes active thermography. So some examples of passive thermography is simply I'm looking at the scenery in front of me, scene in front of me, and collecting information. I'm looking at how it will look like in the visible spectrum and how it will look like in the infrared spectrum to tell us that there is some information that we can get from the infrared images. So first thing is you realize that you can get contrast. So different objects are at different local temperatures, which we can see in color scheme, artificial color scheme. But you can see something called a hot spot or a cold spot, relative variation. We can see that contrast. We can see. You may or may not be able to ascribe a temperature, but you can still see the differences due to various mechanisms. So this is the most useful part of the infrared diagnostic, thermography based diagnostic procedures, that it can give you a quick qualitative assessment of what is going on. And then if you want some more information, quantitative information, you may do some little analysis to get that information. So in that sense, it is widely used in all the industries. So here we look at again emissivity to tell us what to do when the object's emissivity is not good. So I told you that a polished material, like for instance, what you are seeing here is actually a steel material, cups made of steel. They are very shiny objects. You can see the visible photograph showing shiny features, I have to deal with this now. How do I know that its emissivity is low? Can I do something about it? Can I improve its emissivity at least artificially? The way I do that is to put a small tape. The black tape that I am showing you there helps you in doing this. So if you look at the photograph, you see that, as I said, it's a poor emitter because it's a very shiny object. So if you were to look at the infrared okay. Each of these tumblers have different waters at different temperatures. One is having, there are 3 cups there. One cup has cold water, one cup has room normal water, and the other is hot water. By eye, I cannot tell. By visible spectrum, I cannot tell. I have to use infrared image to be able to distinguish this. But I know I am dealing with a poor emitter. So I'm putting a tape. This tape has a very good emissivity, black tape, commonly available tape. So it has emissivity of 0.95. So I put this tape and then look at the infrared image. Now I can make out which is hot and which is cold. I can see that the rightmost cup has hot water, the leftmost has the cold water, and the one in the middle has room temperature water because everything is the same. Room temperature, tape, tumbler, cup, everything is the same. So contrast is not much there. But the contrast is very high and very low, or both are very good at high and low temperatures. So this is a very simple, effective way of helping us find the temperature locally by if wherever possible we put a tape on the object and then make the assessment, and we will be in a position to quantify the temperatures associated with that local region. So that is one nice way, practically useful, and there are tapes available which can withstand different temperatures. Some of them are polymer, so they will all be not more than 150 degrees Celsius, but there are some special tapes which are available which can go to higher temperatures, which you can use for high temperature applications. So the higher the emissivity, the better it is you are in a position to assess the temperature accurately. So there is a definite advantage in having high emissivity. So whether it's intrinsically there or whether I can put it locally, that's the point here. I can, making use of this property of high emissivity surfaces or tapes, I can make use of it and make sure that I get good assessment of the temperature. The only caution here is the tape that we stick, the tape should be very thin. It cannot be a thick block or something like that. So the amount that to quantify that, this bottom graph is giving you an idea of how much thick can I have. If you have something like about 30 micron thickness for the tape, then you are not modifying the object's temperature characteristics. If you go to a thicker tape, then the tape's properties also come in. So that will modify the temperature and emission characteristics as well. So you should go with a very thin tape and you'll be able to get good results. So these are all the effects of the surroundings that may be relevant when we are taking outdoor. If you are in the outdoors and taking measurements outdoors, you will have to worry about solar radiation because they are all additional factors that come into the image that you are capturing. They all will, so the cloud cover will affect it, moisture, if there is anything present, it will affect it, wind will affect it. So you have to be a little careful. So there are some guidelines in the handbooks, ISNT handbooks have some guidelines as to how you should carry out measurements when you are outdoors using infrared passive. These are all for passive thermography. And this is to tell us about what materials to be used when you are talking about capturing images through a window. Windows are probably there in many situations in the sense the object is somewhere in an enclosure and you are outside that enclosure and there is a window, and through the window you are collecting radiation, and you need to make sure that the infrared radiation is not blocked by the window or modified by the window. So there are only certain windows, as we saw earlier, only certain types of materials which will allow for infrared radiation to be transmitted. So we have to take care of that, and only then you will be able to get a good idea about the object's characteristics. Again, for passive thermography. So between the short wavelength and the long wavelength regimes, you will find slight differences in the operational ease. So if you look at for instance, the role of sunlight, you will find that when you do the long wavelength based measurements, the role of or impact of sunlight is very little. If you go to shorter wavelengths, you will have a larger effect. If you go to longer wavelengths, it will be lesser effect. So these are some, again, lot of useful tips that people provide as to what wavelength regime will you choose depending on where you want to make measurements. Are you doing it in the presence of sunlight or cloud cover? All those things, you can make some assessment based and use this information to carry out your inspection. When it comes to active thermography, as I said, there are many ways to stimulate the material. That means to produce heat or to take away heat. I can heat it directly, I can do microwave heating, I can do inductive heating, I can do convective, I can do mechanical rubbing, I can do ultrasonic heating. There are many ways to heat. Because I'm not interested in the actual, I only want to heat the material and let the heat transfer into the material and see how the material is handling the heat transfer. That is what I'm interested in the infrared thermography part. Because I know that the way the heat is transferred in the material tells me about the internal structural features, whether there are defects in it or not. All this information is what I am interested in. So I really do not. So it depends on the context. If inductive heating is allowed, if it's a metallic object, I can do inductive heating. If it's a plastic object, I have to think of some other material, some other way of heating it. So depending on the situation, I can choose to heat it in different ways or take away the heat in different ways and then try to look at the heat transfer characteristics. So can I know how much more time I have? Hello? Okay, fine. Thank you. So I'll try to wind up by. So this is, I will give you just one slide on how this can be done. For instance, when you do a flash, what is called as flash thermography or pulse thermography. So what I do is I switch on, if you recollect, when you go to a studio to take a photograph of yourself, they put some flash lamps and they'll shine light for a brief period and take a photograph. The same kind of approach is done for infrared thermography as well. You shine a heat source is switched on for a very short time, and the heat is falling on this radiation is falling on the object, and this object will now transfer this heat which is on the surface. It goes into the medium, and there are governing equations that will help us understand how this heat is transferred, and there are solutions to these equations. So what you see in the graph here is how the temperature is falling at any one position, one point on the surface. If there is no defect in the object, then the temperature will simply keep decreasing with time. It is plotted in a logarithmic scale here, logarithm of the temperature difference and with the time. So temperature difference with respect to the ambient. So you will find that initially the temperature is very high. We just expose it to a heat pulse. Thereafter, the heat on the surface, the temperature keeps falling because the heat is transferred inside. So as the heat is transferred inside, the surface temperature keeps on dropping. So that is what is indicated by the blue line. But if there is a defect or if there is any obstacle to the heat flow inside the material, then locally the heat is not transferred as efficiently as it is without the defect region. So it will appear to have a relatively hot spot on the surface, which is what we had discussed earlier as well. So it will show up as a contrasting feature. And the time at which it appears, this contrast, this is now I'm doing a movie now. I'm taking a movie out of this real-time monitoring of the way the heat is transferred. So I am watching the surface temperature all the time. I see that certain portions of the surface, the temperature is going to, decreasing continuously. But in certain regions, the temperature is not changing too fast. It's going slowly. That means relatively it's warm or hot. I know at what time I get this. I can see from this graph at what time it is changing from normal to abnormal. But that time tells me at what depth the defect is present. And the contrast will tell me what is the thermal contrasting characteristics of the defect with respect to the medium. So these are the two properties that I can extract from looking at a flash thermography kind of a experiment. I do an experiment like this where I flash a heat pulse and I see the heat transfer from the surface. I monitor the surface temperature and I'm able to see the contrast on the surface and infer the depth of the defect as well as the contrast, thermal contrast between the properties of the defect, thermal properties of the material versus the thermal properties of the medium. So this is just one example of how active thermography can be used to extract very useful information about the object that we are studying. So I'll skip a few slides. There are some more examples of this, but I'll just skip. There are different ways of doing it. This is the kind of sources that are used for heating, and depending on what range of wavelengths you are interested in, you can use these kind of sources. You can use quartz, tungsten tubes if you're doing short wave or medium wave. If you want to do long wavelength, you can use ceramic elements to heat. So there are these guidelines that can help in choosing the what kind of source we want. And we can also look at the pulse duration because it's important to ensure that the pulse is short, and not only short, it shouldn't have a tail. It should not go up and then slowly decay. If that happens, then there is a problem in the analysis. Analysis becomes very difficult. It should be short and like a rectangular pulse, ideally. If then and so these some of the common sources are listed here. They are kind of in from milliseconds to seconds it goes. So typically millisecond pulses are used in flash lamps, and these are useful for certain applications. Each one of them can be, as I said, depending on the spectral range and depending on the flash duration, you can choose the sources for active thermography. And there are many application areas that you can imagine now. There are so many things that can be done using this infrared thermography, either in the passive mode or in the active mode. And you can see that you can look at different features like pipe thinning, moisture entrapment or ingress, heat leaks, anything that is overheating, anything related to material characteristics, or you can look at it as an online process monitoring tool. There are many things that can be done. So with this, I'll stop my presentation. Thank you very much. That, thank you. Thank you very much. So shall I log off? Okay. Okay. Thank you. Thank you.
चाल
Check. So after this basic information on infrared thermography, we'll go to the second lecture. Yeah, and that will be given by Dr. Sharath D. I'll just introduce and then you can go ahead, sir. Sharath D is working as scientific officer at Radiation Application and Metrology section in Safety, Quality and Resource Management Group of IGCAR, Department of Atomic Energy. He has obtained his PhD from Homi Bhabha National Institute, IGCAR Kalpakam campus in 2015. He is working in the areas of infrared imaging and its application in non-destructive evaluation and healthcare and image processing as well. He has published around 35 articles in international and national journals. He is a life member of ISNT and Indian Institute of Metals. So over to you, sir. Sorry, very sorry. We'll have to take a break and then come back.
Sure.
Sorry. There is a tea break and then we'll come back.
Very good morning, everyone. In the previous talk, Professor Krishnamurthy sir has given insight on fundamentals of thermal imaging and heat transfer mechanism, emissivity, etc. In this session, I'll be covering about, next slide, please, more about the infrared camera. So what I'll talk is infrared sensing, where I will cover about detectors and the optics, then performance parameters. So when you are going to choose a IR camera for particular applications, you have to look into some of the important parameters in the specifications. So those parameters we call as a performance parameter. So we will try to understand what are the performance parameters and how to choose an suitable IR camera for your application. Then something about factors affecting the measurement like heat transfer mechanism, correction parameter, etc. Then about briefly about the calibration of the infrared cameras, and if time permits, some standard test methods to evaluate the quality of the infrared images. Next slide. Yeah. So this is the overall picture of an infrared imaging system. So it all starts with the object emitting radiation, and there is an optic system which collects this infrared radiation and filter out unwanted radiation and lets in only the infrared radiation. And there is a detector system which converts this incoming infrared radiation into an electric signal, and there is a readout circuit which converts this electric signal into digital counts. And again, there is a electronic parts or the processing unit where you have the calibration and the correction parameters and image and video processing. Everything will be done in this processing unit. And there is a bunch of sensors inside the camera which monitors the camera temperature, and it recognizes the change in lens, etc. And finally, there is a user interface which displays the image and which allows you to measure temperature measurements. So now I'll just talk about the detector and then I'll go to the optics. Next. Before we go into the detectors, there are some important parameters which you should understand. First one is the time constant. So basically what it tells is how fast is your detector. Basically, this tells the time required for an detector when it is exposed to a abrupt change in infrared radiation to achieve 63% of its peak value. So if a detector has a time constant of, let's say, 0.1 second, and there's another detector which has a time constant of 0.5 second, then the 0.1 second time constant infrared detector is fast. So this is directly related to your frame rate. Frame rate is the number of images you acquire per second. If you have a application where you want to capture fast moving objects, then you should have a detector with a very less time constant. So next one is the noise equivalent power. So noise equivalent power tells about the sensitivity of your detector. So as the name says, it's a noise equivalent power. That means the power of infrared radiation that is required to create signal strength, which is equivalent to the strength of the noise. So if the power of the incoming radiation is less than NEP, then the detector will not detect any, will not be able to make any meaningful reading. So the incoming radiation should be always higher than this NEP. So if, again, let's consider two detectors where one detector has a very less noise, another detector has a higher internal noise. Then the detector with the lower noise requires less power to make measurable signal, whereas the detector with high internal noise requires high power. So the detector with lower NEP is usually has a better sensitivity when compared to detector with higher NEP. Then there is something called detectivity. This is basically the inverse of noise equivalent power. Why we are going for detectivity? Because usually our intuition that higher number is always associated with the best result. But here NEP For a better detector, always it's associated with lower number. So just to make it higher number, we are just going with the inverse of NEP. And the final parameter is the D star. This is derived from the detectivity. So this is one of the important parameter in detector. D star, actually this sensitivity of the camera not only depends upon the incoming power, it also depends upon the area of the detector and the bandwidth of the detector. So D star is mostly it is a normalized parameter. So if you see any detector, you will find this kind of curve. That is the responsivity of the detector. We call it the D star versus function of a wavelength. So this is the different types of infrared detectors. I'll come to this in the later stage. So as you know that in any imaging system, detectors forms the core part of an imaging system. So we call it as a heart of an imaging system. So basically detector acts as a transducer. Here it converts the incoming infrared radiation into electric signal. So here you have to notice one thing is that thermal imaging doesn't measure temperature directly. Here we measure the incoming infrared radiation and then it is converted into a temperature value using calibration process. So now all the detectors comes in the form of a focal plane arrays, FPAs. So these are nothing but the matrix of detector elements. We call as a pixels, which you have seen in our normal visible cameras, right? Similarly, here also we have a array of pixels. We call it as maybe 640 by 512 or 1024 by 1024 pixels. So basically the detector system looks like this. You have a array of detectors which is overlaid over on a iridium bump which connects between the the detector array and the readout circuit. So the detector array will convert the incoming radiation into electric signal and this readout circuit will convert it into the digital counts. There are basically two types of infrared detectors. One is thermal, another is photon or quantum detectors. Next slide. So thermal detectors, these are the two-step transducer. So what happens in thermal detector is the incoming radiation is falls on the detector material. It absorbs the incoming radiation and due to this absorption, the surface temperature of the detector material will increase. Due to the this change in temperature, there will be some change in property. We know that properties like electrical resistivity or thermal conductivity or EMF, all these are temperature dependent parameters. So this change in material properties are related to the incident radiation. So these thermal detectors have a flat spectral response and lower sensitivity, and these are inherently slow detectors. I'll explain about this bit later. There are the different types of thermal detectors are, one is microbolometer. Microbolometer works on the principle of change in electrical resistivity with change in temperature. And there is a pyroelectric detectors. This works with the change in electric polarity with change in temperature. Thermopiles, there's a change in thermal EMF with the change in temperature. And pneumatic detectors, this works with the change in pressure with the temperature. But most of the IR cameras with thermal detectors work with the microbolometer detector. No other detectors are used. In the market, most of the thermal camera works with this microbolometer detector. The next slide. We can go 2 slides next. One more. Yeah. So this is a D star curve I have shown you earlier. So you can see there is a D star curve for the bolometer and pyroelectric detector. These are the thermal detectors. As I told, this has a flat response curve over the wide range of wavelength. That is because it mainly works on the absorption of the infrared radiation. So this absorption is uniform over wide band of wavelength. And also it has a low responsivity compared to the other detectors. You can see it has a very low responsivity. That means sensitivity of the camera. That is because uh, this works with the increasing temperature. So the increasing temperature inherently increases the thermal noise in the detector. Go back to one more. Yeah. So coming to the next type of detector, that is the photon detectors. So these are the semiconductor based detectors. You know that photoelectric effect, whenever the incident radiation falls on the semiconductor, if the incident radiation energy is greater than the energy gap, then electrons from the valence band, it will be excited to the conduction band, resulting in either change in resistivity or change in current or change in voltage. So by measuring this change in the electric property, we can correlate this to the incoming radiation. So now since the energy threshold, it as you can see, the photon detectors generally detects the infrared radiation only if the incoming radiation has energy greater than EG, that is of the band gap. That's why, or else there is a cutoff wavelength for that. If the cutoff wavelength is greater than lambda cutoff, then this detector will not work. Okay, next slide. One more slide. Yeah, so you can see here this indium antimonide and mercury cadmium telluride. These are the photon detectors. So you can see after some wavelength, there is a, it will not be able to detect the infrared radiation. You can see it's a 3 to 5 micrometer. Indium antimonide works very well and it has a very good sensitivity. Why, that I'll come later. So thermal detectors always have a flat spectral response, whereas the photon detectors have a cutoff wavelength. Previous slide. Yeah. So there are different types of photon detectors like photoconductors, photodiodes, Schottky barrier detectors, and quantum well infrared photo detectors. Like photoconductors are mostly uniform semiconductors where incoming radiation will change the photoresistor. Their photodiodes are mostly PN junction diodes where the change in voltage or change in current is measured. And this is the photon detector cooling. I think this is what Professor Krishnamurthy has mentioned in the previous talk about the cooling of the detector. So these photon detectors requires cooling. Why? Because at room temperature, that is around 300 Kelvin, the thermal energy associated with this around 26 milli electron volt. And this is quite enough to cause excitation of conduction valence electrons to the conduction band. So these electron acts as noise because we want only the free charge carriers caused because of the incoming infrared radiation, not because of this thermal energy. So how to avoid this? So to avoid this, what you do is you cool the detector to liquid nitrogen or still lower temperature. By that allows you to minimize this thermal energy and there will not be any noise because of the thermal excitation. That's why all the photon detectors requires cooling. Next slide. Previous. Yeah. So due to this cooling, you can see that photon detectors have a superior sensitivity or the detectivity when compared to the thermal detectors. Next. So here is a small comparison. As I told, thermal detectors have a flat response curve, whereas the photon detectors have a limited spectral response. And thermal detectors have a lower sensitivity when compared to the photon detectors because photon detectors are cooled to the lower temperature. Thermal detectors are best worked for small temperature applications, whereas photon detectors can work for extendable temperature range. Thermal detectors are slower response time because this is a two-step detection process. So inherently it is a slower detector when compared to the photon because it's a direct conversion. And thermal detectors are uncooled, so which operates at near room temperature, whereas photon detectors are cooled. So this cooling is a advantage as well as a disadvantage because cooling will increase your sensitivity, yes. But again, it will increase your, one thing is the cost. Second thing is its size. When you are compare IR camera with photon detector and that with the thermal detector, IR camera with photon detector are bulky. So it is difficult to carry to the field and do the inspection. This is more suitable for the lab applications. Whereas if you want to go for the field application, generally the thermal cameras are better suitable for that. Yeah, this is just an example. I don't know whether it is clearly visible. So this is a thermal image of the handprint on the wall. It is like I have just kept the hand for some time, then I have removed and immediately taken the thermal image, and there's another thermal image after some time. So this is taken using a cooled camera, and this is taken using a uncooled camera. So this shows the sensitivity of the superior sensitivity of the cooled camera. So you can see here, compared to these two images, this has a better contrast. Also after some time, the uncooled camera is not able to resolve all the thermal features here because of the higher noise, whereas cooled camera still is able to detect the finer fingerprints. So this demonstrates the superior sensitivity of the cooled camera. Next. Yeah. So next, moving on to the optics, lens, mirror, filters, and windows, prism, all these uh, parts are called as optics of the imaging system. So here I just want to show you this graph. This shows the transmittance of different IR optical materials as a function of wavelength. For example, if you want to work on some application which involves some windows, you want to procure a window for IR camera, then if you are working in mid-wave, that is 3 to 5 micrometer region, so you can see this uh, calcium fluoride or magnesium fluoride, even sodium chloride, whatever the sir has shown in the previous experiment. So all these things have a good transmittivity in mid-wave infrared region. If you want to work in long wavelength infrared region, then zinc sulfide or zinc telluride, these materials have a better transmittivity in long infrared region. So based on your camera spectral length, you need to choose the window material accordingly. Next slide. So this is just different IR optical materials with their properties and typical applications. You can just go through that one. Yeah. So next in optics, important part of the IR camera is the lens. So lens is it's not a diffractive device, it's a refractive device which focuses IR radiation onto the detector. So there are two important parameters we have to consider. One is F number and another is the field of view. Whenever you see the specifications of IR camera, these two parameters will be mentioned in the specification sheet. So what does F number say? So this indicates the lens capacity to collect the incoming infrared radiation. So for example, if I have a lens with larger diameter, obviously it will collect more infrared radiation when compared to a lens with the smaller diameter. That's why you can see F hash is equal to F by D. F is the focal length, D is the diameter of the your lens. So generally lens with the lower F number collects more infrared radiation. F1 lens is faster than F3 lens. So here is an example. You can see here, this is a 75 mm, F number is 1.2, whereas this camera, its F number is 5.5. The difference you can see here, the lens, this lens has a larger diameter compared to this lens. Yes, F1 lens is faster, but the disadvantage here is it will have a larger diameter and it will not be a compact IR camera. So there is always a trade-off between the diameter as well as I think it's not. It's okay. It's not visible, sir. Yeah. So yeah. Yes. So so that is the meaning of the F number. Next slide, please. Next. Yeah. So next parameter is something called field of view. So field of view is nothing but the angle at which the detector sees an object. Okay. So even our human eye has a field of view. It's around 120 degree. Generally, the field of view is described in degrees. There are two parameters here. One is the instantaneous field of view, another is the field of view. So instantaneous field of view is nothing but the angle over which single detector sees the object. So these two parameters also will be mentioned in your specifications. Generally, instantaneous field of view is expressed in milliradians. So this is given by pixel size by the focal length. If you see a IR camera specification, they will say instantaneous field of view of 0.5 millirad or 0.4 millirad. Next comes your field of view. This is for the single detector, whereas this is for the entire detector array. So how much the your entire detector sees the object. This field of view generally given in degree, whereas the instantaneous field of view is given in milliradians. Next. Yeah. So based on this field of view, we can have different types of lenses. Whenever you buy a IR camera, generally it comes with the normal lens. It will have a field of view of 24 or 25 degrees. Then, there are different additional lenses available, like wide angle lens, then telescopic lens. There's one more lens, close-up lens, which I have not mentioned here. So as this name says, wide angle lens will have a wider field of view. Okay. So for example, it will have a field of view of around 45 degree. Why it is required? For example, I have one applications where I don't have much access here. From here, if I want to capture the entire wall, with a 25-degree field of view, it may cover only this much area if I capture the image from here. With wide angle lens, I can capture the larger area when compared to the normal lens. Then there is a telescopic lens. So generally this telescopic lens will have a narrower field of view. And why this is required? Mostly in electrical inspection, in like a transformer or transformer inspection, where I will be standing here, the transformer will be far away. So there is a one connector has a hotspot. So I want to image that connector alone. With the 25-degree lens, it will capture the larger area. But with the telescopic lens, I can narrow down my field of view and capture the connector alone. So based on your applications, you need to choose the which type of lens you have to use. This is just an example. So this is the digital image of a building, two buildings. So this is the digital image, the thermal image captured using normal lens, 24-degree field of view lens. This is captured with 45-degree, which is wide angle lens. You can see here, it has covered more area. And this image taken with 12-degree lens. So that is the telescopic lens. It has covered only this small area of this building. Okay. And these all taken at the same distance. The camera to object distance has not been changed. Next. Next. Yeah. Now coming to the performance parameter. How do you select thermal imaging camera? So first you should be clear what is your objective. So what you would like to monitor or measure, whether it is a NDT application or whether it is a medical application or whether it's a condition monitoring application. So this objective of your end use, you should be very clear with that. So that, with that, the sensitivity of the measurement, accuracy of the measurement, static or dynamic event, everything will be fixed based on this objective. So now to choose the proper infrared camera for your application, there are some parameters which will help to finalize that. So these parameters you can, if you see any specifications of IR camera, you will see all these parameters like temperature range, accuracy, frame rate, spatial resolution, temporal resolution, spectral range, etc. So we'll see one by one. So first one is the temperature range. This is the important parameter which will decide your IR camera. For example, if I am working on the medical application or condition monitoring application, I need not go for very high temperature range, because medical application hardly we will go above 30 or 50 degrees centigrade. Or in case if you are working in say furnace monitoring or welding inspection, then I have to go for high temperature cameras. So if you are working on a low temperature range, generally long wavelength infrared cameras are suggested, and for higher temperature range, mid wave and short wave infrared cameras are suggested. And that is, this choice is based on, again, by the this is the Planck's curve at different temperature ranges. So this Professor CVK sir has discussed earlier. So higher temperature, you can see the peak wavelength is around shorter wavelength side. So that's why if you want to achieve a high sensitivity, always you should go for mid wave or short wave IR for higher temperature applications. Yeah. Another important parameter is the accuracy. So accuracy will tell about the error in the temperature measurement. So there is a difference between accuracy and precision. I hope you know about that. So accuracy is nothing but the closeness of the measured value to the true value, whereas the precision tells you about the, if I make a repeated measurement, how the measured values are closely related. That tells about the precision. Generally, if you see the specification, IR cameras accuracy will be written like plus or minus 1 Kelvin or 2 Kelvin or plus or minus 2% over the full range. Generally, this plus or minus 2 Kelvin is used for lower temperature application. Like I say 50 degrees centigrade means my accuracy may be 50 plus or minus 2 degrees centigrade. Whereas if I go for higher temperature, let's say 1000 degrees centigrade, then 1000 degree plus or minus 2 degrees centigrade will not make any sense. That's why you should go with percentage. For when you go for higher temperature, the 2% of 1000 is 20. So then my accuracy is 1000 plus or minus 20 degrees centigrade. So that is much more accurate. Next. Yeah. So coming to the next point is the frame rate. Here the integration time, that determines your frame rate. The integration time also will be mentioned in your specification sheet. I have talked about the time constant. That is, time constant is with respect to the detector, whereas the integration time, this concerns the whole process, where the amount of time taken to capture a single thermal image, starting from collecting the radiation from the lens, falling on the detector, creating the electric signal, and converting into digital values. So all this process will combine together, lead to the integration time. Generally, integration time and signal to noise ratio are directly proportional. So if I increase my integration time, my signal to noise ratio will increase. But the problem is, higher integration time means it will lead to the lower frame rate. Integration time and frame rate are inversely related. So there is always a trade-off between integration time and this frame rate. Generally, photon detectors have a faster response time when compared to the thermal detectors, as we have seen earlier. That's why always photon detectors have a higher frame rate compared to the photon detectors. Sorry, compared to the thermal detectors. Here is one example. This is the thermal image of the rotating tire. So this has been, first image has been taken with the thermal camera with 60 frame per second, and the second image of the same tire taken with 1000 frame per second. So you can see the difference here. All the rims can be clearly imaged with higher frame rate, whereas here the rims are not seen. So again, it depends upon your application. There's one more point here. As I told, the frame rate can still be increased with something called sub-window mode. So what is sub-window mode is, uh, the frame rate, it not only depends upon the how fast is your detector, it also depends upon the readout circuit. I have 1000 by 1000 detectors, so it takes some time for the readout circuit to read all the information, right? So instead of that, I image with only 100 by 100 pixels. That means I have lower number of pixels to read. So then my reading time will increase. So that also will help in decreasing the integration time. So by working in sub-window mode, I will be able to increase my frame rate. For example, generally the photon detector thermal camera with 640 by 512 pixel resolution will have a frame rate of 125 hertz in full window mode. If I reduce the pixel to, for example, 100 cross 100, I can capture the image with 1000 frame rate per second. So that is the advantage of sub-window mode. But here the catch is, I will be able to capture only the small part of the image. Next slide. Yeah. The next important parameter is called temperature resolution or the temperature sensitivity. So what it tells is the smallest temperature change at the target surface that can be clearly sensed by the or differentiated by the camera. Okay. So this is expressed as a noise equivalent temperature difference, NETD, in your specification sheet. Generally, it is will be like 0.1 degree centigrade at 30 degree centigrade. So temperature sensitivity, it has to be specified at a particular target temperature. Generally, the temperature sensitivity can range from 0.02 degree centigrade. I think now it has gone still down, like 0.015 degree centigrade for photon detectors, and can go up to 0.1 degree centigrade for thermal detectors. So thermal detectors with lower sensitivity, photon detectors generally have a higher sensitivity. So just to give an example, I don't know whether it is very clear to you. The first image we have, it has been captured with thermal camera with sensitivity of 50 millikelvin, and this image has been captured with the sensitivity of 35 millikelvin. So with the just change in 15 millikelvin, we can see the these features like buildings and all. It was feebly visible here, but in this image, we could detect very clearly. So that is the advantage of having a camera with the high sensitivity. Yeah. Next is the spatial resolution. So generally the spatial resolution is defined by the number of pixels in focal plane array and the field of view. So already field of view I have covered. So I'll just show you the example of how the number of pixels in focal plane array affects your measurement. So these are the image of the same scene recorded with the different pixel resolutions. This is by 1024 by 1024, and this image is with 640 by 512, 320 by 240, and 160 by 120, and 80 by 80. So you can see that the finer details which can be seen here are all are pixelated there. So higher number of pixels in your FPA, better will be your spatial resolution. So if you consider 10 years ago, 320 by 240 used to be a normal pixel resolution. That used to be a good pixel resolution. Now it has come to 640 by 512. Still, these cameras also coming 1024 by 1024, but its cost is very high actually right now. Still it is coming, but currently most of the cameras work with 640 by 512 pixel resolution. Finally, the spectral band. I think Professor C.V.K. sir has covered some of this one. So again, the spectral band choice is based on your application. For imaging objects at ambient temperature like condition monitoring or medical application, long wave IR cameras are preferred, whereas high temperature application, short wave or mid wave IR cameras are preferred. And for outdoor application, generally long wave IR cameras preferred because the interference from the sun's spectrum is minimum in long wave infrared region when compared to the short wave and mid wave IR. And for larger distance, generally the atmospheric absorption is less for mid wave region when compared to the long wave region. So the selection of spectral band should be decided by considering the final application, distance, type of operation, temperature, and emissivity of the medium through which the IR radiation has to pass. Yeah. So this is about the performance parameters. Next, let's see what are the factors affecting the measurement. Emissivity, atmospheric path, surrounding, heat loss, and characteristic of the measuring instrument. So most of the things are covered in the previous talk. So I will just give you a couple of examples here. Next slide. So one example is how heat transfer mechanism like conduction, convection, and radiation is affecting your measurement. Yeah. So here are two thermal images of some electrical components. Okay. So you can see here a hot spot. Here also you can see a hot spot. So here this is this hot spot is due to the reflection, whereas this hot spot is due to the actual overheating. Now, how to differentiate these two? So when there is a hot spot due to the overheating, you know that this temperature will be high, other end will be at lower temperature. So there will be a, due to the conduction, heat will pass from this to the other end. So leading to a temperature gradient. You can see here the temperature is gradually decreasing from this part to this part, right? Whereas if there is a reflection, you can see there is a very sharp boundary you can observe here. So that is the difference between the reflection and the actual hot spot. Next slide. And here is an example of convection. So this is again the thermal image of transformer part. You know that transformer things will be outdoor application. So if you take the thermal image during windy condition, so when wind is flowing, what happens is it will take away the heat from the uh, solid surface because of the convection. So this image was taken during a strong wind condition. So you can see one hot spot here. But when we took the image with the no wind condition, you can see we could detect two hot spots. So this hot spot had a slightly lower temperature when compared to this, but due to the convection, that was not apparently seen in the first image. Yeah, this is a just simple thermal image of a window. So you can see in visible spectrum, we can see through that. But in IR spectrum, what happens is, this is the reflection of the person who is taking the thermal image. So the radiation energy which is emitted by the body, which falls on the window and reflect back on the camera. So this reflection is due to the radiation energy. So another two important things to consider while taking the thermal image. One is the spatial resolution. Whenever this is the thermal image of soldering wire, heated wire, it is a 8 mm diameter wire. So here you can see the soldering wire covers the good number of pixels here, whereas this was taken at a distance of 30 centimeter, whereas this was taken at a distance of 2 meter. So you can see the tip is not very clear here. So the tip is not covering enough pixels. So you can see the temperature as I think it's around 160. Here it is 260. So if you want to get the exact temperature, you have to cover the field of view at least 80% of the field of view should be covered. Okay. Second thing is the focus. Whenever taking the thermal image, make sure that the object is focused properly. So here you can see the tip is very clear. So that means this image is focused. Whereas in this image you can see the tip is not clear. That means it's a out of focus image. So in this the temperature has reduced to 116 degrees centigrade, and though it covers the most of the field of view, still the temperature has reduced because it is out of focus. So whenever you are performing thermal imaging experiment, make sure that the object covers maximum field of view. Second thing is make sure that it is perfectly focused. So in some objects you will not be very sure whether it is focused or not. Then you can keep one sharp object near to that and you can see whether the object is focused. Next. Yeah. So if you want to get accurate temperature measurements, accurate temperature measurement from the thermal imaging, you should incorporate some of the correction parameters like emissivity, ambient temperature, atmospheric temperature, relative humidity, distance. These are the main parameter you should feed into the software to get the accurate temperature result. So why these parameters? Because I think this also has been covered by CVK sir. I will just briefly tell you about that. So the simple scenario is you have an object which is emitting, which is at a temperature of T object. So it emits radiation of phi object. So this will go into the detector. That's what we want. But the problem is this is a real object. So real object always has a emissivity less than 1. So that emissivity correction we have to incorporate here. So the energy emitted by the object is emissivity times phi, that is the radiation of the object in terms of the black body. Then if it has a emissivity, then it has certain reflectivity also. Let's say the object has an emissivity of 0.8. That means 80% of emission, then rest 20% is the reflection. So now this object is kept it with some surrounding. So let's say it has kept near a furnace. So furnace is at higher temperature. So 20% of the radiation from the surrounding will be reflected towards the camera. So you have the, along with the radiation of the object, there is a radiation which is reflected by the surrounding. Okay, the surrounding temperature is T ambient. Then this radiation has to pass through the atmosphere. Now the atmosphere has certain transmittance because of the water molecule present in this and the distance between the camera and the object. All this lead to the some loss in energy when it is passing through the atmosphere. So when the if the transmittivity is tau, when the radiation reaches the camera, there will be some loss. So that loss also we have to taken into account. So there is a loss due to the atmospheric transmission. There is an additional noise due to the surrounding reflection, and also the atmosphere itself will emit some infrared radiation. That also will be detected by the infrared camera. So that's why the detected infrared the radiation detected by the infrared camera will be combination of the radiation emitted by the object, reflected by the atmosphere, and the ambient and emission from the atmosphere. So to get the exact temperature value from the this one, next slide. So we have to know the object emissivity. What is the ambient temperature? Ambient temperature is the temperature surrounding the object. And what is the atmospheric temperature? That is the room temperature. And what is the atmospheric transmittance? So this atmospheric transmittance, it is not a direct value. Generally, This atmospheric transmittance depends upon the relative humidity, atmospheric temperature, and the distance between the camera and the object. So when you give these parameters to the software automatically calculates the atmospheric transmittance. That's why these are the important correction parameters you have to feed into the software to get the accurate temperature measurement. Yes, if you are interested in emissivity measurement, most of the emissivity values will be available in the literature. You can get it from the literature. But if you want to measure the emissivity of the material or any surface, so what you can do is you can stick a tape, small tape to the surface of the object which has a like black tape, which has a very high emissivity, and measure the temperature over that tape and measure the temperature over the object. Now you adjust the emissivity in the software. Software allows you to change the emissivity. So you decrease the emissivity till the temperature of the tape and the temperature of the surface matches. Okay, so that is the emissivity of the this one. Same this one, instead of tape, you can apply the black paint. There is also there's another method. What you can do is you measure the actual temperature of the surface using a thermocouple, and you measure the temperature using infrared camera, then decrease the emissivity till the temperature of the surface and that of the thermocouple are matched. So that is the emissivity of your surface. And more destructive method is this is mostly for the civil application they use. Drill a hole in the wall. So generally the hole will act as a black body. Cavity acts as a black body. So the temperature over the cavity can be taken as a reference, and it can be used to derive the emissivity. Yeah, coming to the calibration. So you know that the accurate relation between the camera output and the incident radiation. So how to derive that? That is done through the calibration. And also the calibration relates the camera output with the temperature. So how to do this calibration? Generally this calibration is done using a black body source. But you know that ideal black body sources are, it doesn't exist. Okay. So we have to create artificial black body whose emissivity is very close to 1. So we will not be able to achieve black body source whose emissivity is exactly 1. Always it will be slightly lesser than 1. There are two types of black bodies available. One is called cavity type black body. So CVK sir has mentioned about this, about the Kirchhoff's law. So what Kirchhoff's law says is perfect absorber is a perfect emitter. So if you make a surface, a perfect absorbing surface, that means you made a perfect emitting surface. So this can be achieved by carefully designing some cavity holes. What you do is the incident radiation, you make sure that it undergoes multiple reflections before it leaves the surface. During each interaction, the energy will be absorbed by the cavity wall. So by this way, you can achieve almost 0.999% emissivity. And there is a, but the thing is, this is the cavity wall. So you have a smaller aperture. So if you cannot calibrate the entire camera. For that, generally we go for with the flat type surface black bodies. What do? Is we coat the surface with the high emissivity material, but this will have flat type black bodies. Generally they have a relatively low emissivity when compared to cavity type black bodies. Next. So how does this calibration procedure it is done? So what you do is you put the camera and the black body in a temperature chamber, temperature controlled chamber, cover the entire field of view of the camera with the black body source and keep it very close. The distance between the black body object and the camera is kept very close, so that the atmospheric transmission is neglected. So what we measure is the signal, output signal from the camera as a function of the radiance of the black body. Now this is integrated over lambda 1 to lambda 2 is nothing but the spectral range of your camera. If it is long wave IR camera, it may be 7 to 14 micrometer. If it is mid wave camera, it can be 3 to 5 micrometer. Based on the detector spectral band, this lambda 1 to lambda 2 is determined. And this output, signal output, depends upon other two parameters. One is R lambda. This is nothing but your responsivity of the detector. This is what we have seen from the D star plot. Okay, and also it depends upon a camera constant, which depends upon the lens, filter, etc. So if you change the lens of the camera, so you have to make sure that the camera is calibrated again for that particular lens. Whenever you change the lens of the camera, make sure that your camera is calibrated for that lens. But nowadays, all the cameras comes with internal sensors. All what they do is they will store the calibration files for different lenses inside the camera itself. So whenever the lens is changed, there will be a sensor inside the camera which detects the what type of lens it is, and automatically it calls back the calibration file and gives you the accurate value. But you have to make sure that the calibration file is stored in the camera. If not, then the calibration has to be done for each lens. Next. Then you measure the signal output at different temperature and radiance values and at different distance, etc. Then you generate a calibration curve. That is nothing but radiance versus the digital count. Next slide. So if you see that this is the radiance, that is the radiance of the black body, and this is the digital counts. This is the output of the camera. So you can see there is a linear relationship between measurement, that's the digital count, and the radiance. But you can see here the top axis is the black body temperature. So the black body temperature and the radiance or the digital count are not linear. So here you can see it's a 10, 20, 30 and 40. So it's not linear. This is because as per the Stephen Boltzmann law, what it says is energy is directly proportional to the fourth power of the temperature. So energy and temperature are not linearly related, but it's a quadratic curve. Yeah. So another concept is you will hear if ambient drift compensation. This is more prominent in infrared camera with thermal detectors, which operates at room temperature. Now the camera detector will be kept inside a housing which is surrounded by other electronic components, and you know that during the operation electronic components get heated up. So when this electronic component get heated up, they will emit IR radiation, and if it falls on the detector, okay, so that will act as noise. Okay, so these are called parasitic radiation, and they causes a signal offset, okay, which affects the calibration. Now how to overcome that? So to overcome this, what they do is they keep a sensor inside the camera which continuously monitors the inside temperature, and it sends the information to the processor, and the camera so then the camera output is corrected for any parasitic radiation influence. So when you do the calibration, they do for calibration for different detector temperature also, not only the temperature of the black body, temperature of the detector also will be varied, and they do the calibration. So based on the temperature of the surrounding detector surrounding, the camera calibration will be adjusted accordingly. This is the last topic. This is called some standard test methods. These test methods are used to evaluate the image quality of the infrared cameras. For that, generally we use something called 4-bar target. So you can see here 4 alternate bars are there. So one is white and one is black. So this will be this will give you the contrast modulation. What you do is generally what we'll do is we'll take a aluminum plate or steel plate and we create through holes through this. So these and all are what you can see is through holes. And the bar height and the bar width, there is a relation. So if bar width is L, the bar height should be 7 times the width. That is, there should be a 1:7 ratio. So if I reduce the width of the bar, then automatically the height also will be reduced. And the distance between the consecutive bar is 2L. Okay. So what we do is generally we keep this plate in front of the black body, and through these holes we weave the black body. So this acts as the source and the black part acts as the background here. Yeah. So before we go to the 4-bar target test, if you want to this NETD measurement, generally this is defined by the camera manufacturer. But if you want to measure NETD by yourself, then you should have a black body source for that. What you do is you keep the black body source at desired temperature, at what temperature you want to measure the NETD, and make the temperature measurement for some period of duration. Here we have taken 1000 images. Okay, so you have 1000 points. So if this was maintained at 34.5 degrees centigrade, so if there was no noise, we would have got a very straight line here without any fluctuation. But since there are inherent noise associated with the director, you can see there is a fluctuation in the temperature measurement. Now, if I take the normal distribution, the frequency distribution of the this temperature measured temperature value, so the standard deviation, generally the 2 times this standard deviation gives you the NETD. Okay. So this is the one way of practically measuring the NETD of your camera. Next slide. Yeah. Now there are 3 test methods I'll just discuss briefly. One is the modulation transfer function. This is generally done for any imaging sensors. What they do is here MTF tells about the how the modulation of contrast is from the object is how well it is mapped to the image plane. So this is the 4-bar target which is kept in front of a black body source. Now what this yellow region is the black body source which is seen behind the this 4-bar target, and the dark regions are the surface of the black 4-bar target. So this acts as a background, whereas the black body source acts as our target. So when I draw a line profile across the 4-bar target, so you can see this for uh, this 4-bar target has a lower spatial distribution. So these are very far, and when compared to this one, these are very close. So this has a higher spatial frequency when compared to this, and there are other two which are still closer. So this has the highest spatial frequency. This is the lowest, and this is the lowest. So we have 4 line profiles across 4 different 4-bar targets. So you can see the lower spatial frequency, the background temperature is around 60 here. So you get a very good contrast curve whose temperature is around 60. And as the spatial frequency is decreasing, still here the temperature is 60, but for higher spatial resolution, you can see here the temperature is not exactly 60, it is coming down, and we are not able to resolve the this contrast here. So if you plot this modulation transfer function, it is calculated using this formula. So you can see here as the spatial frequency is increasing, your modulation transfer function comes down. So if you have a camera with very high sensitivity, then we will be able to measure this, resolve this contrast very clearly. Next slide. Then there is something called minimum resolvable temperature difference, MRTD. There is a ASTM standard for this. You can refer this standard. So this combines the what you call is, this is called compounds systems ability as well as the observer ability. The thermal imaging has to be analyzed by an observer, right? I have to analyze or you have to analyze. But my what you call the visual, this one is different from the other person. So if one person is able to see this hole, other person may not be able to see that small hole, right? So this MRTD combines both the system ability as well as the observer ability to distinguish the pattern. So this is nothing but the minimum temperature difference in a standard bar target by observing the display on the monitor. So we slowly increase the temperature of the black body and see when this 4-bar target appears. Okay, so you can see here at this 0.2 degree variation, this 4-bar is appearing for me slightly, and but the other bars are not seen. Okay, so like that, when we slowly increase the temperature, you can see the next set of bar is appearing. Then similarly, if you increase the temperature by 0.5 Kelvin, again small next one is coming. And when you increase it to 10 Kelvin, you can see all the things are clearly visible. So as the spatial frequency is increasing, the MRTD also increases. For a very fine, what you call the spatial frequency, you need higher temperature difference to distinguish it. Next slide. The last one is the minimum detectable temperature difference. This is similar to MRTD, but without the any 4-bar. So previous slide, please. Excuse me. Previous. Yeah. Previous slide. Previous one. Yeah. So you can see this is a square block without any bars. So this we use it for the evaluation of MDTD. Yeah. So again, it's the same thing. You can see here with the increase in temperature, at what temperature you will be able to distinguish the black body. So that temperature we say is the MDTD. So this temperature may different for different person based on their visual capability. Yeah. Yeah, that's all. Thank you. If you have any questions, I can answer. Yes. Excuse me.
Hello. Sorry, as you say in last slide,
Yeah.
if there is change in temperature, the image quality of photo is changing. My question is that there is any like a thermal gradient and resonance of the energy can deviate the focus point of effect.
Pardon me. Again, can you come again?
Thermal gradient
Ah,
and resonance of energy can deviate the focus point of
radiance
effect.
of the energy.
Yes. Resonance of energy and thermal gradient can change the focus point of effect.
Focus point.
Yes.
No, that mainly depends upon the optics only, sir.
Sir, what is the interval or duration of recalibration?
Camera calibration you are asking.
Yes.
So generally it depends upon the calibrator whoever gives. For example, if you do it at NPL, National Physical Laboratory, New Delhi, they will give the validity for 2 years. So like every 2 years, then you have to do the calibration.
And during examination, what is the interval of recalibration? Like if we are changing only optical lens, then we have to recalibrate, or
Yes, so when you do the change in the optics, you have to recalibrate the camera. Once you recalibrate that, then I'm telling once in every 1 year or 2 year, you have to calibrate the entire system.
during operation, if camera is giving feedback, like you have explained,
Yeah.
is giving feedback like thermal gradient is increasing
The
or
ambient
resonance
drift
is
compensation.
then we need to recalibrate it.
No. Then that
Only
automatically will be taken.
adjustment of.
Yeah, that will be automatically taken care by the camera software itself. What we have to do is we have to do the external calibration just to make sure that your camera has not drifted too much from your accuracy value.
Okay, it can also give the feedback before starting the environmental condition of room or lab.
That we have to do it manually. That is for the getting the accurate temperature from the uh, infrared image.
Means we have to measure the
Yes.
atmospheric
So if
condition.
you want to get the accurate temperature, you have to measure the relative humidity of the room, the room temperature, what is the surrounding temperature, what is the distance between the camera and the object.
Okay, thank you, sir.
So if you give these parameters, then we can get the accurate temperature measurement.
Okay, sir.
So any other question? No questions? Okay, so in that case, sir, it was a most engaging lecture. So thank you very much for giving this lecture, and we would always call you upon whenever we require. Thank you very much. So as a token of love, please accept this. Now we will break for lunch, and we'll come back, say within half hour or maybe 45 minutes, not more than that.
Mobile I'm keeping here. Anywhere it's fine. From here also it's. Once pointer is working or not. Laser pointer. Not working. That LED.
राहुल सरांकडे आहे पटकन घेऊन ये मी थांबतोय तोपर्यंत you want the slide
If pointer is there, it's beneficial. Otherwise, I can explain like that. Sorry, just give an indication 10-15 minutes before. So small demo I will show it to them.
will take maybe 1 hour.
That's more than enough. Just 10 minutes before you just give an indication. I will stop there.
पटकन लाव
No, no, it's not working.
that will not be visible sir, because we had tried during
Okay, okay, fine. As
but
slides,
then
it's working.
slides
No,
होईल
slides also not working.
ऑन केले का ते
Yes, okay, fine.
करा
आपल्याला पॉइंटर बघायचंच नाहीये
Slides, if
स्लाइड
it works,
वाढवा
that's
पहिले
कळशी पॉइंटर चालू होता ना
पॉइंटर चालू होता त्याला वरती करावं लागलं
केलं ना खाली करावं लागतं हे
that is off.
तो ऑन तिकडं
स्लाइड तर इकडे तिकडे व्हायला पाहिजे ना पॉइंटर सोड
हे घेतलं का त्यानं ट्राय घेतला पेन
Otherwise, it's okay. You can see the slides.
सगळं
मगाशी चालू सर सर घेऊन
Slides at least, if it works, that's fine.
ओके
you can tell him he will
That's better. We'll start.
सोडून द्या जर ते PhD So good afternoon all of you. चालू केले? Yeah. So we'll start with the third lecture and I invite upon Professor Ravi Babu Mulavisla. Welcome sir. I'll Professor Ravi Babu received MTech from National Institute of Technology, Tiruchirappalli in 2000 and PhD from Center for Applied Research in Electronics, IIT Delhi in 2007. His research interests include thermal, acoustical and optical methods for non-invasive imaging, non-destructive testing technologies. He serves as editorial or advisory boards of several referred journals of American Institute of Physics, Institute of Electrical and Electronics Engineer, Institution of Engineering and Technology, Elsevier, Taylor and Francis, Springer, Nature, etc., and also to several peer-reviewed conferences. So over to you, Ravi.
Very good afternoon. Now my job became very easy because of the very nice talks of Professor C.V. Krishnamurti as well as Dr. Sarath. They covered everything, so from there, it's working. So all the fundamentals covered by Professor CVK and detailed specifications as well as the camera details and the thermographic sensitivity and the performance, all those things, excellent talk by Dr. Sarath. So it made my life very simple. Just I will explain some of the widely used NDT techniques. Okay, mainly I will concentrate in this talk on active infrared thermographic techniques rather than the passive approaches. Because if something gives enough thermal gradient to see, then the passive thermography is good enough. But most of the NDT applications, you want to look for a deeper defects of a smaller sizes. Then in that sense, one has to rise the temperature gradient over the surface so that we can detect with enough thermal, whatever the gradient that it is giving with enough sensitivity. So for those type of things which gives a faint indication or a very small thermal contrast on the object surface, for those type of applications, always active thermography is preferable compared to that of the passive thermography. So as far as the things are concerned, mostly I will concentrate on the active thermographic techniques, not only restricted to these domains, but it is having a wide variety of applications in different domains. But I will restrict myself only to the composites because nowadays you know that thing, the Airbus, Boeing, all these people almost more than 50% of the aircraft with CFRP and the GFRP materials, mainly the fiber reinforced polymers because of their own advantages like very good impact capabilities, sustaining, and very good strength to weight ratio and the fuel consumption, all these things by considering most of the aircrafts as well as some of the shipbuilding industry also going towards the composites, GFRP because of the low cost. And we will concentrate on these materials and we will try to see that thing how the active thermography is useful for finding out the internal defects. And the second one I will consider that thing for the marine industry, that is the corrosion monitoring and all those things, mainly for the ship hulls. These two topics I will give more emphasis. Nevertheless, it is applicable for more or less all the industries. Fine. Before going to that, I am not going to discuss anything, the fundamentals, how the IR imaging will be, how the thermography will be carried out, because we have detailed lectures on that. Okay, the fundamental physics by Professor C.V. Krishnamurti sir, and after that followed by the specifications of the camera, how to choose and how to, what will be the sensitivity requirements, what will be the resolution that we are expecting, the optics behind, everything Dr. Sarath explained that thing very nicely. So here I will concentrate mainly on the NDT schemes, what are the different active approaches and what are the widely used techniques at present and their advantages as well as some of the limitations of those and how we can address those limitations in order to get better sensitivity and resolution for the given technique. And after that some of the results and followed by discussions. And this is the typical experimentation setup, looks like this one. These two are the lamps. As Professor CVK said that thing, we have a wide variety of excitation techniques. We can heat the sample by induction. We can go for a halogen lamps if you want a large area, if you want to inspect. Then the induction heating or a ultrasound heating, those are the localized heating mechanisms. We can heat a small portion of the sample. Suppose if I want to see what is happening, a large object, it may be a ship hull or it is something like a wall. Then for that, giving a whole field or a full field heating mechanisms are useful because it is less time consuming. So here more emphasis I will give to the optical heating because the advantage is large field of use that we can see. and more or less independent of the material thermal conductivity or specific heat, you can go for this. Okay, there is nothing like a perfect insulator to heat. Of course, depending upon the duration that you are heating, it has to conduct. So by considering the advantages, if you are going for a microwave, then that will be useful only for certain type of materials. Okay, you can do good for composites because they can pass through. But if you want to do a metal, microwaves can't penetrate. Similarly, if you want to do ultrasound heating mechanism, then it is a localized. You have to couple the transducer horn to the material, then you can excite the sample and you can see the heating mechanism. But optical heating, large areas, few meter square areas you can scan or you can detect or you can inspect in a very less time. So mainly I am going for optical heating mechanism. Of course, this is also having some of the limitations that I will give emphasis on those also along with the advantages. These two heat sources you can modulate in a required fashion. Suppose if you are having the sample is thin, then you can go for a simple like a flash. You give a small duration of the order of milliseconds to few seconds depending upon the sample thickness and its thermal properties like conductivity, specific heat, density. Based on that you can choose the duration of the pulse and the peak power requirements. But if the object is too thick, going for a short duration pulses, it will not help because it may not go, sample will not get that much heat input in a small duration. And if you are increasing the peak power, and all the drawbacks are the sources will be costly, and it should have the response time like that. Even though if you are giving a microsecond pulse, the lamp should respond. If you are going for these halogen lamps or something, of course this is LED lamp, but if you are going for a halogen lamps, they will have their own thermal inertia to rise its temperature up to that level and come down. So it will exponentially rise and it will fall down. So the duration you can't keep minimum. Then if you are not keeping the duration minimum, then you will not get the better resolution. That we will discuss in the coming slides. As I said, that thing most widely used already Professor CVK has mentioned that thing, most widely used is pulse thermography. A short duration pulse you give onto the sample, you on these lamps, a short duration pulse onto the sample and try to monitor the temperature distribution. If you are having a high speed camera during the on time also, if we don't have, generally we use it to observe that thing, a low frame rate camera, generally cooling cycle. That's why pulse thermography, especially flash thermography, people use it to call that one, that is a cooling cycle, because the duration of the pulse that you are giving, the flash of the order of few milliseconds. In few milliseconds, if you are expecting sufficient number of frames, then the camera frame rate should be of the order of kilohertz. So that will be a costly affair. Then the response time of the detector, everything will come into picture. So it will increase the cost, system cost. So if you are going for a pulse thermography, we use it to treat that is a quick and fast inspection. In fact, it is not true because you are not monitoring during the on time and you are monitoring during the off time. So the off time, definitely how much time that you are capturing depending upon the thermal properties of the material as well as its thickness. If the thickness is huge, then if you are capturing the data in a very small duration, you are losing. Because the deeper defects, it will take more time to cause the thermal gradient on the surface. It is similar to whatever you use to feel that ultrasound. If the defect is deeper, it will take more time. Okay, the wavefront will go up to the defect and it has to come, it will take its own time depending upon the distance. In between, if I am stopping the capturing or the data acquisition, I will lose that defect. I will not get any indication of that one. So in the same way, in the flash thermography, if the material is thick, then even though we are telling it is a fast technique, it is not true. Otherwise, you have to sacrifice deeper defects. And second thing is the material is thick enough, so the thermal wave, they can't penetrate whatever the power that you are giving in a small duration, even though if you give, the average power is very less. So you can't see deep inside the test objects. These are the drawbacks. Otherwise, it's a good technique as well as the resolution for the surface defects are concerned or subsurface defects very near to surface. Excellent resolution flash thermography will give. There is no doubt because you are probing higher frequencies. Higher frequencies will cause a shorter wavelengths. All we know that thing, whatever the probing wavelength and whatever the defect size, lateral dimensions that you are seeing, those should be comparable. If you are using a long wavelength to see a smaller dimension object, it is not possible. Okay, buildings you can see few meters or whatever the height with a longer wavelengths. If you want to go for the atomic distances, you can't use microwave, you can't use the IR, you can't use the visible, you can't use ultraviolet. You have to go for X-ray because the X-ray wavelengths of the order of angstroms. So the interatomic spacing is also of the order of angstroms. So if you want to see the interatomic spacing, the wavelength should match. That is the concept. You can use more or less the same way the total electromagnetic spectra as well as the mechanical spectra also. The wavelength should match what sizes that you are expecting to detect the defects inside it. If you are sending a longer wavelength, you will lose both the resolutions. That is applicable for depth resolution or that is applicable for spatial resolution. Of course, more or less we use it to speak. The spatial resolution depends upon the pixel distribution. If you are using 1 megapixel, 2 megapixel, 10 megapixel, 30 megapixel, 30 megapixel will give a good spatial resolution. But yes, that is true. If it can provide the thermal gradient on the surface, it can detect. If that is not there, whatever the resolution that you are using, how many number of megapixels hardly matters. Because the gradient is not there. Surface gradient is not there. Yeah, that is the meaning. If you are taking it in a dark room, whether you use a 100 megapixel camera or you are using a 2 megapixel camera hardly matters because the light scattered is insufficient to get the exposure onto the film or onto a solid state detector. That is true everywhere. Then in order to overcome the high peak power requirements of this pulse thermography, people have gone that thing, why can't we heat more time at a particular frequency? You elongate the duration of the experiment and reduce the peak power by keeping the average energy same, the area under the curve is same. That is all about the lock-in thermography. But in previous days, they used to use the quadrature phase shifting. That means every cycle they use it to take 4 or a 2 depending upon the sensitivity that you are expecting, and they use it to reconstruct the phase image somehow. Always it is believable, the results are believable if you are taking the time delay or the phase. The cause is very simple. If I am speaking here, just if I am listening the loudness, in order to estimate the distance, that may give a false alarm. Because it is not guaranteed the detector is taking from the back wall or the detector is taking from here. Suppose both of them, if they reach the ear detector, in some particular path lengths it is traveling, but here they are constructively getting added up. The path lengths are like in such a manner, they are coming here, they are getting constructively added up. Then what will happen? That thing I will feel a loud sound. Suppose the path lengths are like that, they are destructively interfere, then I will listen nothing. Then what I feel that thing, there is no echo. No, actually the reflected echo is there, that one and remaining multiple, somehow they are making the phase condition, net resultant intensity is here is 0. That doesn't mean nothing is reflecting back. That you can see that thing, the fading effects and all those things also. Whenever you are taking the mobile to some places, you will feel a 0 signal. Then you will walk that side and you will see that thing again signal will come. So this interference effects which causes a nil signal or a full signal, all these things, but actually the reflected signals are coming, but they are not constructively added at the detector. So all these artifacts are there if you take the magnitude information or simply the raw thermal profile that you are taking or the raw signal if you are taking. But one thing is true, whatever the multiple reflections comes, whatever the interference taken place doesn't matter, but the time delay, I can say if something is coming from there to here, the time delay will be more. Something, if it is coming nearby, the time delay will be less. If I can differentiate the time delay, then never I will lose the information. Definitely I can tell irrespective of whether it is constructively or destructively interfere, that will cause only the variations in the amplitude. But if I take the time delay, definitely that will be a larger path length that is traveling. This is a shorter path length it is traveling, I can tell if I take the time delay. So time delay will give a faithful way of interpreting the data. If someone is taking the time delay, that's why in ultrasound also mostly, even though DSC curve is there, but taking the amplitudes we will not believe that much. We will believe time of flight. The time of flight mainly depends upon the depth information. Amplitude, it may be corrupted by noise or it may be corrupted by any other interference effects. So the time delay is the best approach to estimate the depth of the defect. The same, if I am asking a question like, if you are having a 1 second duration cycle and you are getting a reflected echo with respect to the transmitted 1 second period, it got delayed by 0.25 seconds. Okay, 1 second is the duration of the signal that I am sending. The echo is coming with respect to the transmitted signal, the echo is having a delay of 0.25 seconds. If I tell like that, or if I tell in another fashion, that is like it is having a pi by 2 phase difference. Okay, if the signal duration is 1 second, then 0.25 is the delay, that means 2 pi by 4. Okay, because 1 second divided by 4 is 0.25. So the total cycle is 2 pi radians divided by 4, that is pi by 2. So if I tell pi by 2 or if I tell 0.25 seconds delay, both are same. Pi by 2 radians difference or 0.25 seconds delay, both are identically same. One way I am telling that thing the radians, that is the phase difference, and another way time delay, but both are identical for a given period of the signal. So once if I know the period, then if I speak in terms of the time delay or in terms of the phase difference, both are identically same. They will never get affected by all these external effects up to some extent of the standard deviation of the noise. Of course, if you go beyond some limit, nothing can be. So that is the thing they use it to consider in case of a lock in thermography, the phase difference, and they use it to identify the depths of the defects. And this is the main problem of the lock. In earlier people used it to use a sinusoidal modulation, and some people started using a square wave, but the fundamental component in that also, how to choose, is mainly depends upon the depth of probing and the thermal properties of the material. Nevertheless, the harmonics will have negligible effect because they are not having enough magnitude. If you take the Fourier series, square wave if at all if you are using such an approach, just elongate in time, in the frequency domain if you see, much of the probing energy is concentrated to low frequency content. That means again low frequency means larger wavelengths means smaller defects, smaller separations you can't see. So just increasing the duration of the pulse just to reduce the requirement of peak power is not a choice, because you will get a very poor resolution because most of the energy is concentrated at the low frequency and if you see the frequency response. So this is not a correct way of doing the things. Then what is the remedy for this? Next slide. Okay, fine. Suppose in the frequency domain, unlike a sink where the higher frequencies are rapidly decaying, you probe in such a manner that thing in the frequency response should be a rectangular fashion. That means the initial frequency you choose depending upon the sample thickness, the lowest possible frequency, then you are ensuring that thing the thermal waves are propagating up to the thickness of the sample, because the no defect you can expect above the surface, below the thickness. Okay, within the thickness only the defect will be. So the lowest possible frequency depending upon the sample thickness, of course its thermal properties, and the highest possible frequency, what is the resolution that you are expecting for the near surface defect. So the highest frequency is the near surface defect and the lowest frequency is how deep the sample is, what is the maximum thickness. In between continuously if you vary the frequencies, if you send with a constant magnitude, then all the depths you are propagating. No depth you are missing. So if you modulate the source in such a manner, if it gets a continuous band of frequencies and all the frequencies are having the equal magnitude unlike a sink, then you will get a continuous depth scanning. You will never miss any defect lies at any depth inside the sample because your frequency is sweeping, so the depth scanning is possible. That thing how to realize what type of excitation that I have to give it to the lamps in order to relay or in order to feel the frequency response is rectangular. The frequency is rectangular means the frequency response, two types of excitation should come into the mind. First thing is whose frequency response is rectangular. If you use a time domain representation as a sink type excitation if you give to the heat sources, then the frequency response is a rectangular. But the sink, you have seen that thing, again it needs a high peak power for the main lobe. So that is not a very correct way of answering the problem. So giving a sink type excitation, again you need high peak powers. So what is the other alternative is modulate the sources in a linear frequency modulated manner. And the initial frequency you choose depending upon the sample thickness and the final frequency what resolution that you are expecting for the near surface defects. In between if you sweep, you are ensuring that thing no depth is missing inside the sample. Okay, if you speak in a pulse thermography, sometimes we use it to speak about the blind frequencies. And all these problems you can eliminate if you are going for a continuous frequency sweeping. Because one frequency may be a blind, but the adjacent frequency is not so. So on an average you can give at least you are not missing any depth or any spatial dimension of the defect. All of them you are detecting. Of course you will get a question that thing, this larger wavelength if I am probing at the time, what will be the resolution for the deeper defects? If the two deep defects are very near, can I detect or not? That question you can see at the later stage because the frequency is very small, it is probing more depth. But at that time the wavelength is also too large. Then how can you differentiate the distance between the two nearby defects if they are located deep inside? That is one question mark if you are using a conventional post processing like a frequency domain analysis. That we will address that thing. In frequency domain analysis, that is the drawback. If you are taking the Fourier transform and if you are taking the phase of a particular frequency component, whenever if I am telling the frequency is fixed. If the frequency is fixed, wavelength is fixed, then again resolution will be a problem. Even though if I probe band of frequencies, any time if I am analyzing only one particular frequency component, again resolution is fixed. As far as the experimentation is concerned, I can climb that thing, I am sending continuous band of frequencies. But whenever analysis, one particular frequency component's phase, that means wavelength is fixed. If I go for another frequency component, again the wavelength is fixed. That means it is underutilized. Whatever the band of frequencies that we are probing inside the test sample, we are not taking the full advantage of the linear frequency modulated excitation. So how to overcome that we will see. So as far as the things are concerned now, in a single experimentation, we are probing the band of frequencies. Unlike a simple lock-in thermography where the sinusoidal modulation, there you have to repeat the test at different test frequencies. Here in a one run, you are completely scanning the sample, depth scanning is possible. So there is no need to repeat the test at different test frequencies. At the same time, the same bandwidth you can give in 100 seconds, you can probe the same bandwidth in 1000 seconds, in 10,000 seconds. So the independent of the duration, your resolution of the test is getting fixed. Test resolution does not depend now on the duration of the excitation. But whereas in a pulse thermography, if you give a long duration, the resolution is poor because the energy is mostly concentrated towards the low frequency, not towards the high frequency if you are elongating the pulse. But here, independent of the duration of the test, you can get the same resolution because the probing bandwidth is same here, independent of the sweep time. The initial frequency and the final frequency, that difference, final minus initial, that is always fixed independent of the sweep duration. You can give a long duration if you are having a low peak power. You can sweep in a less duration if you are having a high peak power sources. So the same sources, whatever in your lab, you can use, unlike a pulse thermography. If you are using a FM, you can use those things for thick materials, thin materials without sacrificing the resolution with a low peak powers as well as in a single experimentation. That is the advantage of these linear frequency modulated excitations. And as I said that thing, you can go for a conventional post processing for this, you can retrieve the phase image. But I said that thing, the phase image obtained at a particular frequency. Particular frequency means particular wavelength. Particular wavelength means again depth resolution is a problem with this type of analysis scheme. It is like you are probing all the, if I am speaking over a large bandwidth, but your detector at a time, it is doing some spectrum analysis and it is allowing only a particular frequency. That means probing at a large bandwidth has no sense. If the detector can respond only one frequency. Then again if I speak again at another frequency it may respond. Then what is the meaning of probing a large bandwidth if it is responding at a time only to one frequency component? So if you are doing such a post processing, then your resolution will be fixed independent of the excitation that you are using. So this is not a, even though one of the widely used promising technique is now the frequency domain analysis, but it is having this limitation. Okay, if you are doing a frequency domain analysis, any phase gram if you take, the wavelength is fixed there. Then this is the thing that I kept in a little bit complex language, is the redistribution of the supplied energy, associated frequency components, whatever you are picking or whatever you are probing, the total energy is redistributed to that concerned frequency components. Then what exactly the issue is, the probing energy is not utilizing. Total probing energy you are not utilizing. Any time you are taking only the associated energy to that particular frequency component whose phase you are analyzing. So this is not a very good way of doing the post processing, again limiting the resolution. Long waves that I am using, I am probing a band of frequencies, but every time I am analyzing I am taking a particular frequency. That means what happened to the remaining thermal wavelengths? At the time I am not utilizing them for analysis purpose. Then what is the way to improve really the depth resolution? And I want to utilize the total probing wavelengths or spectral weight or the probing frequencies without missing any one. Every frequency component should contribute to detection of defects located at different depths. All the frequencies always I want. Then compared to going to the frequency domain analysis, do the analysis in time domain itself. Rather than distributing the energy to the individual frequency components, concentrate the energy. Okay? total, you compress the energy to a localized time interval so that the total energy will be utilized. It is simply like this. If I am having a VGR here, somehow I generated violet to the red. Then if I keep some glass plate whose thickness I want to measure, then if I am keeping a photodetector here, at any spatial point only one wavelength is coming. Compared to that, that means the resolution is fixed, because any spatial point if I keep a photodetector, in order to measure the thickness of the glass plate, I am seeing only one wavelength because this is a VGR. Compared to that, why can't we keep some dispersive element here like a prism between the glass plate, VGR and prism? Then the total energy now concentrated, it is coming like a white light, a spot that will have a more intensity rather than any individual color intensity. If you say take, if you compress that one to a localized spatial point by keeping a prism, the total energy is utilized at each time. Then you take the glass plate thickness and keep another glass plate thickness, then the delays will be different. This white will shift to this position. And if you keep a thicker, then the white will come to the new spatial position. So if I measure how this white light is shifting over the spatial positions, I can calculate the glass thickness. The same way here I am concentrating the energy, don't bother about the matched filtering and all those things here, but I am supplying the energy to a long duration like this, I am concentrating to a localized duration. Very small interval, all the frequencies are coming, like VGR is coming, total this is occupied this much spatial distance. Now if I keep another prism here, then I am concentrating to a very, very small spatial point, that is the white light. That intensity will be very high, the spatial point is very, very small compared to the VGR whatever it spread here. So you concentrate the energy rather than splitting the energy. So each and every, whatever the defect is there, next compressed pulse will come with some time delay and some less amplitude if it is a taper. And another taper defect, whatever the reflected echo is coming, that will be, it is similar to that of the ultrasound what you are using. Okay, this is the matched filter approach in ultrasound. You can see that thing, if from each and every depth, if the depth is too far, the defect depth, then it will be little bit attenuated and the time delayed. So this peak will shift towards the right depending upon the depth of the defect, and the amplitude will fall because of the attenuation offered, because it is traveling longer paths. So if you measure either this correlation coefficient, the peak, or you measure the time delay, then you can calculate the depth of the defect, because you know what bandwidth that you are probing, you know the thermal velocity of the thermal waves. So the group delay you can calculate that thing because you know the group velocity. So you can exactly calculate the depth of the defect by using a low peak power heat sources, unlike a pulse thermography, and in a single experimentation, unlike a lock-in thermography. So this will enhance the spatial as well as the depth resolution for a given spatial resolution of the camera. This is the approach that we use it to follow to reconstruct this thing. Here we will get the compressed pulses like this, and here we will get the time domain phase. And we introduced in another way compared to doing the phase in the frequency domain, where I said that thing, the wavelengths are fixed. Here you go in such a manner that thing, take the phase in time itself. Then at least the frequency components are not separated. Then the resolution will be better. That you can see in some of the experimental results I am going to present here. Okay. Fine. These are some of the advantages of time domain approaches. Whatever the bandwidth that you are using in the frequency domain, it will split the spectra. That means any phase gram, if you take at a particular frequency, the wavelength is fixed. In a time domain, those limitations will not be there. Frequency domain, you are splitting the spectra, whereas you are concentrating the energy in the time domain. It's localizing to a very small interval of time. So the depth resolution will also be improved, test sensitivity will also be improved. And you can ask that thing, the question will come, why can't we do the same approach for conventional techniques, correlation based approach? We can do that thing for the lock-in thermography, we can do for the pulse thermography, but these are not pulse compression favorable schemes. So they will not concentrate the energy. Okay. If someone is having a doubt, then you can ask me at the later stage because it's much more involved about the signal processing. So I don't want to give much here that thing. Because pulse compression, if I am having a VGR, suppose one prism, if I am keeping here a white light, if I am keeping here white light and a prism, then I will get a VGR. Then this VGR, if I am allowing only one particular wavelength, if I keep another prism in spatially inverted, can I get a white light here? I will not get. If I want white light here of a very small spatial dimension, I have to send all these wavelengths to the prism. If I block any particular set of wavelengths, I will not get here a white light of a very small spatial dimension. Concentrated energy I will not get. If you filter it out, that is the thing. In another way you can say, if you want a direct delta function in the time, the bandwidth should be infinite. That is a simple way of telling. If the bandwidth is not infinite, then you can't construct an impulse in the time. Okay? So, bandwidth should be in such a manner, it should be as much as possible in order to get the concentrated energy either in the space or in the time. That thing is the important. These are not pulse compression favorable. If I send a green light through a prism, the other end is also green light. If I send a red, the other is also a red. But if I send a white, this is a VGR. If I keep another prism here in an inverted direction, again I will get a concentrated white light from this VGR. But that is not same if it is not a white light. It is only green means here I will get only green. Here I am keeping only red means here. All those composite things if I keep, that means spectral width if I increase, then only I will get the concentration of the energy here. The same principle, this is having only one particular frequency, so the thermal wavelength is also fixed and it can't concentrate the energy also, because only one particular spectral component. The same thing is true for, because these, even though band of frequencies are there, these are not systematically arranged to get a compressed pulse, so the response will be something like a triangle. Here also you can see that thing, the triangular envelope inside whatever the way that you are modulating the source at a particular frequency. But if you choose these type of excitations, these are pulse compression favorable excitations. You can see that thing, the energy concentration to a localized duration. Here if it is 100 seconds, a small portion of that is displayed here. It is occupying the total energy is coming of something like in a 2-second span. 100 seconds, whatever you supplied, that is coming in a 2 seconds. And the same thing here, higher order side lobes, we deleted those things. I mean, we suppressed those things by giving some envelope functions to this one. And similarly, if you increase the bandwidth, it will be localized to very small duration. If it is an infinite bandwidth, this will be a direct delta function. If it is a direct delta function, any two very small durations you can differentiate, because the width of this one is approaching to 0. So any defect very nearby, two defects are there, their delays are of the order of microseconds or nanoseconds, still you can see the separation between them, because this concentrated energy is occupying a very small duration. So how nicely you localize the energy, that much nicely you can differentiate the time delays. How nicely that you can differentiate the time delays, that nearby defects you can easily detect. Very small differences in the, that means the resolution of the test will be improved. And the sensitivity anyway will be improved. If I keep my hand here at the VGR, I will not feel the burning sensation. But if I keep a prism here in opposite direction, once the white light comes here, if I keep my hand, it will burn. That means localization of the energy will improve the sensitivity, because signal strengths are improving. So these are some of the widely used pulse compression favorable schemes. But if you see in any scheme, if you go that thing, there is some amount of energy is leaking to the side lobes. Okay. Suppose if you can concentrate this energy also into the main lobe, then you will get the high signal strengths. That means the test sensitivity will improve. And see, these are some of the experiments that we have done on carbon fiber and glass fiber reinforced polymer samples, and of course the sandwich structures also mostly used in aerospace. You can see that thing, this is a carbon fiber reinforced polymer material, this one, first one, because of the brightness it is not, the contrast is not good here. So you see that thing, these are the different diameter holes, blind holes, Those are inside, from one side it is visible, another side, these are the blind holes. Okay, you can see that thing, the depth resolution here, an excellent depth resolution, not only the spatial contrast. This is because of the pulse compression. You will get an excellent time resolution or a depth resolution as well as the spatial contrast. But whereas if you see that thing more or less is true for a glass fiber reinforced polymer, but these are not the blind holes, these are the delaminations artificially introduced. At a different layers we kept some Teflon patches to mimic the delamination. Then we try to see that thing, the shape also you can see that thing, the depth resolvability as well as the spatial, in both of them the shape and as well as the distance information is preserved because all are coming at this almost the same time instant. Same time instant means their depths are same. Then some of the sandwich structures, these are also artificially introduced delaminations by inserting the what is that, Teflon insets. This is a honeycomb structure. This is the honeycomb. This side is a carbon fiber reinforced polymer. This side is also carbon fiber reinforced polymer. And somewhere the adhesion properties we made like that, somewhere it is missing that honeycomb. And somewhere between the honeycomb and the front face sheet, we introduced the delaminations. Those things are very clear here. You can see the contrast obtained from these. These are the Teflon things. Here the honeycomb is missing between them, so you can see the contrasts of those things. So the advantage of this one compared to ultrasound or something, there you need a couplant or you need an immersion technique mostly. And even though if you tell that thing nowadays we are developed, we are having the air coupled or something like that, still it is a point-wise technique. It will take its own time. If you are going for a few meters per area, if you want to test or inspect in a less time, it's almost impossible. Okay, it will take its own time if you are going for ultrasound. If you are, you can say that thing, I am having a technique like an X-ray imaging or a radiography. Then the problem is in fields you can't apply that much easily because the radiation things involved. That is not suitable for the field tests. But the thermography, even ordinary conditions you can apply that thing. Large areas you can scan. Suppose the flight is landing. At the time you don't have much time to take to ultrasound, or you don't have much time to take to the X-ray, because you can't, even though the people are inside the flight, still you can perform the thermography, there is nothing wrong. If any abnormality comes, that localized region you see with the some of the quantitative technique like ultrasound. Okay, best approach is in a no time you can see almost all large areas with the thermography. Okay, fine. You can see some of those things, the depth resolvability you can, I think I should go there. Can you please? These are some of the impact damages on composites. You can see the depth resolvability as well as the spatial contrast that you obtain. Here whatever it is there, that one is the time, that is frames whenever if I am telling, is the time information in the time domain analysis. Whereas if I tell frames in the frequency domain analysis, that corresponds to bin number, that is corresponds to some particular frequency. Next slide please. Next one. Next one. This is the first one is the, you can see that thing. These are the phase grams obtained that thing. Sorry, this is the cross correlation coefficient, but this is not for a pulse compression favorable scheme. It is simply a pulse thermography which is not a pulse compression favorable scheme. Next one. Next please. Next. Just you observe the things compared to telling. Just come. Next. 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 Okay, next one is also fine. Come down. So you can see that thing, the depth resolvability in a pulse compression favorable scheme. Okay, fine. You can start this. Sometimes that is working, sometimes this is working. That is the frequency domain analysis. You see the frame direction, there is no depth resolvability at all. Whereas if you are coming to the time domain phase, please click. you see the axis in the z direction. That will give the time information. You got a very poor resolvability. Please. Here you can see the depth resolvability in the time direction, not only the spatial contrast. That is the advantage of the pulse compression favorable schemes, and it's a very, very, very good resolution compared to that of the conventional frequency domain analysis. Next, please. Click all of them, no issue. Oh, not that much quick. No, okay, fine. Can you play one by one? Can you play once again that movie? Okay, you minimize this. Okay, fine. That's better. First one also. Third one also. Simultaneously. You can see this is the correlation coefficient where the pulse compression is taking place. That is the time domain phase, relatively okay, but not this is superior. The last one you see the frequency domain phase analysis. What at present, this is the world most acceptable approach, widely used approach, and they use it to tell a better depth resolvability with the frequency domain analysis. It's very clear it is not so. How it will be possible? If you see theoretically also, these are the frequency components. It may detect at a one particular frequency or a second frequency or third, but all the frequencies they can't give the continuous depth scanning. If you see that thing, somewhere the drawback is the wavelength is fixed, particular phase gram they are taking, they are claiming it is an excellent, no, it is an excellent contrast provider, but not the depth resolvability. Even though phase variations in a given frame, you may get variations over the defect phase, that you can't claim the depth resolvability. That is the thing just I want to bring to your notice. This is the best resolvability. Next please. I think we don't have time. Let me give a small demonstration of a real sample so you may appreciate compared to going for the, okay, conclusions after that I will do. Sir, I will take 3 more minutes. Can I sit sometime here? It will take time, little bit, it's software. If you see all the processing techniques simultaneously I am comparing, individually if you see they appears like this. Okay, each frame I am taking in the pulse phase thermo, whatever the phase analysis, and the time domain phase TDP and cross correlation coefficient. But if you want to really see the depth resolvability, seeing a single frame it will not help. Seeing a single sample, you can't say time delay. Okay, you have to have all the samples to tell a time delay. And you can feel the same if I am doing that thing. Okay, all the frames I will not do because it will take time. You can see the depth resolvability there. See that thing, excellent 3 defects you got. That you are missing in the conventional widely used at present in all the industries as well as the labs are following the pulse based thermography. You can see that thing, those 3 defects, whatever is there. So, sorry, this one is creating issue. Let me show. Then you can see all the faces, not only that one. This is the last one, sir. I will not take much time. Just I want to see for the sample all sides. Okay, what exactly, where exactly the defects located. You can feel the depth resolvability in the cross correlation coefficient, whatever matched filtering or whatever the terminology that I am using, the concentration of the energy to a very small intervals. You can see very clearly the defects here. That is lagging, whatever, this is the world most conventional, widely used technique. People will believe that technique like anything. Of course, we are trying to tell to all the scientific people, it is not true, because scientifically the wavelength is fixed, how you will get the resolution? That is the thing, that is our work from last 20 to 21 years. These are our contributions to thermography. Thank you very much for your attention, and feel free to discuss if anything is there. All these things we developed here indigenously. Okay, nothing we have taken, just of course the algorithm of the people, okay, whatever they are using, we have to take that to compare our technique. Any quick questions? After that also you can interact if you feel.
So thank you very much, Ravi Babu. So it was a good lecture, and what was good was again the movie that you have shown. So thank you very much on that. I would also call upon Shop NDT because they are also leaving, so we would give them a token of appreciation. Thank you very much for coming here and interacting with all the people here. So we'll continue our promotion partnership henceforth also. Thank you. We'll continue. There are 2 more lectures, and both are on the applications. So the next 2 lectures will be given by Menaka Madam, and after her first lecture we'll have a short tea break and then come back again for the last lecture, and after that there would be demonstration. So I'll introduce her. She is actually the representative of PFMB and the program coordinator for this. M. Menaka, a postgraduate in physics and has over 23 years of experience in the field of NDE for material characterization. She has specialized in the areas of thermal imaging, image processing, and digital radiography. She is presently heading Radiation and Metrology section of Radiological Application and Technology Division in Indira Gandhi Center for Atomic Research. Is it? It is IGCAR only. No? But then here some typo is there. Okay, fine. Her field of interest are material characterization using thermal ND and thermal imaging as diagnostic tool in healthcare. She is an ASNT certified level 3 in infrared thermal testing. She has more than 100 publications in international and national journals and 90 publications in conferences. She has more than 1226 citations for her credit. She has won the Best Paper Awards during IIM NMD ATM 2005 and ND 2007. She has also won the Best Chapter Award in R&D category for the paper published in Journal of ND, that is ISNT Journal. She is recipient of Group Achievement Award of Department of Atomic Energy for the year 2009. She has been bestowed with Science and Technology Excellence Award by Department of Atomic Energy for the year 2020. She has guided more than 10 engineering and science postgraduate students in their projects. She has been active member of ISNT Kalpakam chapter for over 20 years and was a member of technical committee for 14th APC NDT. She is a member of QIRT Asia 2015 steering committee and has been a regular faculty for level 2 and level 3 courses that have been conducted by ISNT Kalpakam. So over to you, Menka madam. Please. Thank you.
Good afternoon to all. Thank you, sir, for the kind words. I need to go there. So the next two presentations would be on application of thermal imaging for condition monitoring and for material characterization and material evaluation. It will be mostly an applications on different components and instruments and processes. So it will be mostly images which I will be sharing and discussing how we evaluate these images to find out the fault which is present inside the component or the process. Okay. So for the first presentation, thermography as a condition monitoring tool, as we all now learned completely that thermography is a non-invasive technique and it uses very little time to map the whole field of view within few seconds and it gives you an output as an image. So which helps you in visualizing the processes or the fault in a better manner. So that's why this becomes an extensive tool for diagnostic purposes and for condition monitoring purposes. Here in this condition monitoring tool, I have mainly highlighted two applications. One is electrical industries, another is in process industry, particularly you can take any oil refinery process or boiler furnace related process systems. So these are the two main systems which I would be discussing in that. Of course, I have just put some images on other application as well, just to give you an idea how this can be applied for other condition monitoring purposes as well. Coming to the, as I first said, this is extensively being used for electrical inspection. More than 50% of its application is in this industry. So That's why we need to know how it is being applied for electrical industry for finding out particularly thermal faults. Why thermal faults is of interest to us? Because there can be possibility of fire accidents and can cause a big catastrophe, and both production loss and the stoppage of because of the accident you can have a loss of financial losses. So that's why this thermography for electrical inspection becomes very, very important. Okay, what exactly we do? As rightly said by Dr. CVK sir in the morning, there are two things. One is qualitative measurement, other is quantitative measurements. Both qualitative and quantitative measurements are being used in this industry. I'll show you where we are using very qualitative information for understanding what is the defect which is present, what is the fault which is present in the component, and further to find out the severity of the problem, we use more quantitative information from the images to arrive at the severity of the problem, particularly in electrical installations. So first, I will be talking about qualitative information. What we are doing there is gathering the information of infrared radiation that is emitted by the electrical system and observing the infrared radiation, recording their finding, analyzing it and presenting in information. So what are the exceptions here? The exceptions here are the warm components. Any abnormal temperature rise are your potential problems. So that's where you are interested. But actually there are some components which will show you, which will appear cold. That will also equally important for you in the case of electrical. But people in large talk about the warm components which may cause a potential problem. Why this is very important? These exceptions are identified and comparing it with the thermal patterns of the like components. That is, if I have a similar component nearby, I do a comparison of temperature between that and tell that, okay, this appears to be faulty, and how much is the severity of the faultiness of, or that is also arrived at. Okay, mainly when you talk about electrical maintenance, it is loaded electrical infrastructure. You can do infrared inspection on a live system itself. That's the biggest advantage. And so that means in a loaded infrastructure, what could be the possibility? Overheating could be the possibility. Overheating because of so many problems. There's poor connections, overloads, phase unbalance and faulty contacts. So these things would lead to the material degradation, production stoppage, operating losses and fire accidents and so on. So these are the things which we are recording because of the overheating, and this may cause these kind of damages. So this is what you are trying to see in electrical maintenance using infrared thermography. So what are the benefits? Here actually both predictive maintenance and preventive maintenance both are being done. Predictive maintenance here actually allows you to schedule the report. For example, as I said before, I try to find out what is the severity of the problem. Based upon the severity of the problem, I go for my scheduling of my maintenance. So in that way, it will help you in predictive maintenance. Preventive maintenance, suppose it has some very high rise in temperature, that could be there could be a possibility of a fire accident, then it could be a preventive maintenance. So both predictive and preventive maintenance can be done using thermography, and these things what it reduces? It reduces the downtime, of course the repair and blow up, and any kind of process stoppage of the production. Of course, then what are the components I can inspect using thermography in the case of electrical installations is any kind of transformer, switchgear, disconnects, bus ducts, control panels, rectifier, drivers, capacitors and so on. I will be trying to give you some examples on each one of you so that you get an idea how it looks for a transformer, how it looks for a control panel or a bus bar. Okay. What is the role of the camera? It will help you in identifying the decisive elements and facilitate you to save time and increase safety. That's the idea of using the camera for the electrical maintenance. Then how do I do my scanning? So this is the very, very important. There is a methodology which we do. Scanning of the entire electrical installation when the elements are in normal load. That is usual load that is taken by the circuit should be there, and you should try to locate spatially all the anomalies present in that is overheating which is present in it. You can actually calculate also and ensure that this is the number which you have to get, or this is the number which is more than what you have calculated. And so you can actually measure, spatially locate your thermal anomalies and definitions of the extent of emergency and the management. That is what I told about severity of the, so the extent at which the emergency is required and management of my thermal faults can also be done using this. So coming to the thermographic systems, for starting from power generation to distribution, what are the things we can do and how, what is its effect? Definitely cost effective, quickly locates you the hotspots which is present in the system. Severity of the problem can also be identified so that you can take up the maintenance appropriately at that time. And how soon, that means it gives you clear idea about whether the repair requirement is there presently or can I take it later on. So it gives you the idea that the equipment should go for a repair or I can take it up later. So coming to the other common applications in electrical, starting from the electrical distribution to transmission lines and loose connections, this can be extensively used. Okay, what is the basic principle behind using this for electrical inspection? We all know that H is equal to I square RT, where T I have conveniently removed here. For this, our understanding, we will take this I square R. So definitely when an resistance increases in the this one, my heat emission is going to vary if the current load remains the same. So when I is kept constant, the resistance varies, means the heat emission on that particular component is going to vary. So when the heat resistance will change, high electrical resistance is the most common cause of thermal heat hotspots in the electrical equipment. This can be because of a loose contact or because of any kind of electrical problem, potential problem. There will be an increase in the change in resistance which will lead to a change in the heat emission. So that's how we try to find out the premature replacement of the equipment also could be detected in this. So condition monitoring in electrical appliances, electrical industry, starting from the power generation to distribution station, this can be used. This is a typical thermal picture of carbon brushes in the generator side of our Madras Atomic Power Station. This you can see that these are the worn out carbon brushes, their temperatures are very high. So those kind of carbon brushes which is used in the generator side of the electrical, this one has been inspected using this, and the worn out carbon brushes were identified and replaced. Similarly, this is the high voltage side of the 230 kV transformer on the generator side. So this is again one shot, and this is another thermal picture of a different 230 kV transformer. So you can see some hotspots which is present because of the improper cooling of the transformers. So, and these are the overhead transmission lines. So these can be used for the distribution stations as well. So this was done on Tarapur station, I believe. So the overhead transmission did not have any kind of hotspot. That means they are very healthy. This is the bush top of again a transformer where you can see the temperatures are very high. So that means when this is a temperature which is recorded on the surface of the, please do remember whatever you are measuring in thermography, that is actually the surface temperature of an object. You are not seeing something which is deep, but that should manifest as a change in temperature at this surface. So that means if the surface temperature is this high, it was around 170 degrees Celsius, I believe. So when we opened out the metal conductor, it was actually partially melted. So you should be very careful in your doing your analysis as well. So similarly, this is a bush top of another transformer. This is actually the insulators. You can see that spurious reflections because of the sun at the insulators, and this is an LPAD circuit breaker of a 230 in the distribution lines. So I think it is in 33 kV switch yard. So this is, so starting from the power generation to the distribution station, thermography can be used extensively for the electrical industry. So as I said before, when you keep the H is equal to I square R, there are two parameters, right? I told about the resistance, change in resistance, which calls a change in the heat emission. There is one more parameter in that, right? Current. you should be very careful that what is the load it takes, and when you do a comparison also, you should be very careful on the load it takes. So you should actually note what is the load as well. This is one of the inspection which we did in our 33 kV switch yard. You can see this is actually appearing as if it is hot, but if you just look at the temperature scale, it is actually 42.3 degrees Celsius is the maximum. This is not energized. This we just took in the evening time. So you should never go by the color of it. That's what Sir Morning told. It is a pseudo coloring. So in the picture it is appearing as if it is hot. But if you just look at the temperature scale is 42, which is just because of we have taken this in a sunny day. And so you can see that this is not energized. The same component, when we energized and took it at two different current, that is, one is at 300 amperes, another is 345 amperes. You can see there is a variation in the temperature. So that means when I am doing a comparison, I should ensure that the current load is the same as the one which I did previous. When you are doing any kind of follow-up or trending studies particularly, you should have the same current value in the system to compare the temperature value with the previous or your recorded follow-up. So you should be very careful when you are doing this recording. And one more important thing which I don't know whether you saw, this is at 16:50, that is 6:15 in the evening, and this is 10:30. So that also has some impact on the values. This is maximum is 114, this is 116. So you should be very careful about two things. One is the load which goes, of course, from the morning they have been clearly emphasizing on the surroundings at which you are recording your inspections. So similarly, in another component of the 33 kV switch yard, you can see that in the L-pad circuit breaker there is a hotspot which is given. 76 is the temperature which is recorded at 300 amperes. For the 345 there is 78. So you should be very careful, and you should record as well. So similarly, we did it on an electrical panel, which is a closed electrical panel. This is a graph which I would like to show, so that if I change my current, my temperature also changes. So I should not compare something which I measure with 300 amperes and compare something with 200 amperes and tell that there is a fault, which is, then you are misinterpreting your data. So you should always note down what is the current which is taken by the component as well. Okay. Coming to the condition monitoring, some of the applications which I will be talking about, it will be more on images. So the excessive heating of a connecting clip due to deterioration. You can see there are 2-3 connecting clips, but in one, because of excessive heating, the deterioration has happened. So that is recorded here. And similarly, overheating at the connection part of contact, because of the high increase in contact resistance, your definitely resistance is increasing, heat emission will be higher. So because of which you are getting a overheated component here. Similarly, this is a disaster failure where the leaking of an isolator took place, and you can see the fire accident has taken place, and that has been recorded here. And when you have a very complex systems, like for an electrical system, you have too many components in one area and you want to identify. So the picture-in-picture effect, that is both diffuse, thermal and visible, to get an idea where exactly the component and which is the hotspot in that too complex area. Okay. Similarly, for fused switches, apart from finding out the fault as well, you can use it as a tool to ensure whether the repair work has been done properly. So this is a digital picture of that. Of course, there is loss of clarity. Before repair, you can see there is a hotspot in one of the fused switches, but after repair, you can see that they have repaired it properly and it is all set. So repair quality also can be checked. Similarly, for an unbalanced loads in electrical circuits, you can see these are 3 phases in which same current is flowing, but you can see that in one alone there is an high excessive heating. That is because of the unbalanced load. So which actually supposed to have the same loads at all the three, but because of the unbalanced load, you are seeing a overheating in one of the phases. Similarly, excessive heating in a defective electrical connection on a station, substation. Similarly, this is another interesting before repair and after repair, but there is an exception here. What is that is before repair you are seeing some hotspot at the top of the electrical component, but after repair you can see there is a hotspot in the bottom. Since the temperature was very high compared to this one, this appeared cooler when we did the initial study. So this was appearing as if this is as hotter, and when we repaired this, we found out that there is some kind of overheating which is happening at the bottom as well. So sometimes you will be recording such kind of things as well in electrical installations. This is again, when you talk about transformers, again we generally do the investigation both in high voltage side and low voltage side and bush top of the 230 kV transformer. We would usually detect for improper flow of cooling oils. If you look at the transformer, the main challenge would be improper flowing of the cooling oils. How do I address that? You can see that this oil which is present, the oil level actually we are able to detect here, which should flow through the fins. If it is not uniformly flowing, you will see a different pattern. I think you have, yeah, here I have. So you can see that there are, so here there is a hot spot and these are the fins where the oil is not flowing. So because of the improper flowing of the oil, you are getting a hot spot somewhere and a cold spot somewhere. And when we repaired it and saw that, then you find out that the pattern is very uniform. Similarly, can you go back to the, yeah. So similarly, the oil level can also be detected using these infrared cameras. So this is again a 230 kV bush top. Here you can see there is a spurious reflection which is caused by the sun because it's an insulator. So ceramic insulator where the sun's reflection was picking up and appearing as if there is a hot spot. So you should be very careful when you are doing the image interpretation when it comes to these kind of, this is again the bush top transformers, and this is the carbon brush owner one. Again, this is on a 230 kV transformer connector side where we again detected a hotspot here. Coming to the transmission lines, you can check new transmission lines or aging joints, fittings to reduce the life components in the transmission line. Of course, resistance over the joint can raise the temperature in the joint, cause a phase drop. Hot joints are located in the transmission lines and estimate the overheating. So these are some of the problems which is faced in the transmission line side, which can be detected using thermography. So okay, this is on the transmission line side. You can see that there is a hotspot which is detected in the here and here, and after repair you can see that this is appearing normal. Similarly, in the connector side, bolted and nut, because of the loose connection, increased resistance will be there. Because of that, we will have an increased heat emission in these kind of areas. So again a hotspot detected in the connector region. This is the overhead transmission lines on, this is again hotspot detected in the connector regions. That both the connector regions, you can, these are the ones which you compare it with the one which is adjacent, because they both should take the same load. When you come, if you don't have any kind of previous records, you can compare it with the component which is adjacent to it and try to see which is the hotspot which you are detecting. That is to find out what is the thermal fault which is present, and to determine the severity, what you do is you have measured this as maximum temperature for 41.6, then this is at 53.3. So you take a difference of it. there is a severity table which is given by the standard. So you can measure depending upon what is the temperature difference between the sound component and the defective component. You can take a call on immediate attention, or whether you can postpone it for the next shutdown. So similarly, it's a connector. Again, here you can see that 48.6 is the temperature which is recorded, whereas in this connector, your recording is for 65.3. That is almost to 20-degree raise is there. So similarly, we do the comparison and give the severity of the problem as well. So this is for one of the connector where we recorded 67.6, and again similarly in face pad clamp. This is an LPAD circuit breaker which I showed you in, but this is an interesting story here. This is actually, we thought that initially it is because of loose contact, we are having some overheating and we are detecting some hotspot here. But what happened is we tightened all the bolts. While tightening, one of the bolt went, it literally got broken, and so we replaced that with the new one. That's why you can see the difference in the color in between the bolts. This is actually a new one, highly reflective, so it is showing a lower temperature. So whereas these are the one which is already little bit oxidized, and this one, so that is showing at a different temperature. But actually here the major problem was corrosion. So this LPAD circuit breaker started corroding, and because of the deterioration of the element material, it again started showing hotspot. So we replaced the LPAD circuit breaker in that situation. So we, until now, whatever we were talking are inspection of the electrical system which is present outside. That means outdoor inspection, and some of the electrical panels as well we have inspected. But if I have closed electrical panel, how do I do the inspection? Then I cannot open the panel and do the inspection. Then I have to mount something like this. Today morning, everybody was talking about IR window. This is what is the application of this IR window. They use an IR window through which they keep the IR camera and measure the components which they feel that is risky to open up and do, where the full load inspections can be done, and of course in a guarded condition. And you can actually, wherever your 90% trigger of arc triggers are there, these kind of inspection are there. An infrared window is installed on that panel, and through the window all the infrared inspections are being carried out. Wherever you have this arc problem, people try to do through using an infrared window for the inspection. Okay, now we go into the process industry. In process industry, you name any of the process industry. It can be steel, refinery, cement, paper, or any mechanical components in any process industry. This is extensively used. In steel industry, this is actually a ladle which is carrying a hot steel. So the refractory lining losses in the steel could be detected here. And the ladle could be clearly detected. This is actually a refractory lining losses, and this is a tubes which is inside the furnace in a refinery, where they are looking for the temperature of these tubes, whether any hotspot is there or any coking problems is there in these kind of tubes which is inside the furnace. And the cement, similarly, this is in a cement kiln where there is a refractory lining losses here that could be detected using tomography. In paper industry, they use this technique for finding out what is the moisture present which is present in the paper. So they allow certain percentage of amount of moisture in the paper. So to detect that, again thermography is used. For any mechanical components, for be it pulley or a motor, this can be extensively used. Here actually it is an worn-out belt which you are seeing as a hotspot here, and here improper winding of motor is there, that has been detected. Of course, similarly misalignment and all can be detected using tomography. This is one work which we did for our heavy water plant Thoothukudi. There, this is actually the thermal picture of the complete ammonia cracker. You can see that this is the complete ammonia cracker unit this is a digital picture of it. We just took the thermal picture of it. So you can see that it's a whole hot process which is going on for heavy water production, where ammonia is cracked and heavy water is produced. This ammonia passes through these cracker tubes inside this furnace. So actually there are burners and flue gases which is present. What we have to do is to estimate the temperature of these cracker tubes for to find out which are the cracker tubes I need to replace. So for that, as morning we discussed, the main challenge here is that we will be receiving, this is at a very high temperature. You have a flue gas which is present, which is at a different temperature, and you have a burners which is very close to it. Again, that is at a very high temperature. But I want to measure the temperature of these cracker tubes. That's how this equation comes into picture, where morning we all the people have discussed on this equation, saying that you do the correction for all these things. You try to understand how the flue gas affects your measurements, how the burners affect your measurement, and try to find out what is the cracker temperature. So this is how we did to find the skin temperature of the catalyst tube for its replacement. Another problem is particularly in the furnace tubes of inside the burner or furnace, actually is the coking problem. Here you can see the pipe is actually choked completely. So because of the coke deposition, and you can see there is a complete blockage here. So this can be clearly detected using thermography, and a hotspot which is developed because of that can also be detected using thermography. Similarly, wall thinning problems. This is actually a zircaloy tube where we have intentionally made 20%, 10% and 50% wall thinning in the zircaloy tubes. When you allow hot water inside it, or we did actually only hot water here, even that gave a very good contrast for us. For 20% of wall thinning could be clearly detected in this case. Similarly, if you have any kind of hot fluid which is going through it, you will be able to detect the wall thinning which is present in it because of the contrast which you are getting. Similarly, this is extensively used for insulation losses and energy audits. This is pigtails where you can see there is a insulated pigtails, whereas these are all pigtails where either the insulation has been deteriorated, and the deterioration of the insulation is also varying here. So severity is also varying. That could also be detected using that. So because of the degradation of the insulation, what is happening? The energy loss is happening. The heat which have to be secured in that component for maintaining that process is now getting lost through through these insulation losses, which is not allowed. So that could be clearly detected using thermography. Similarly, this is a ladle which is again causing a in a steel industry. Again, refractory lining losses has been done. Here you can see a hot spotted. After the repair, again we did an inspection of that and ensured that the repair work is good. Similarly, we can use this for insulation linings in burners, boilers and furnaces. And similarly, the efficiency of desalting and cleaning. So suppose if you have desalted or cleaned these furnace tubes, then how much is the cleaning has been done and how much of efficiency is there, you can clearly detect using thermography in these kind of process industry. Similarly, for the refractory lining losses, this is again a refractory lining losses in the heavy water plant Thoothukudi in the cracker unit. You can see that this is how the refractory lining losses is happening and how the heat losses is happening in the system was calculated, and we did the necessary repair work for that. And similarly, in any kind of furnace, these are some of the, this is one of the furnace at which the base there is a deposition as well. So that could be clearly detected. This is a miscellaneous actually system in which some hot thermal anomalies were found detected. That could be clearly detected. Here similarly, deposition in the vessels. That is again a serious problem in these kind of process industries, where you can see that apart from detection of levels, you can actually see what is the deposit which is getting deposited at the bottom of these kind of vessels. That is what is detected here. And coming to the storage tank, you can detect the storage levels of storage of in the tanks, level of the liquids stored in the tank for any kind of liquid. How it is detected is based upon thermal capacitance, as rightly said by Sir CVK sir in the morning. The heat capacity, the amount of heat energy stored by the liquid and the air which is present top will vary. So which will in turn give you a thermal contrast, which helps you in detecting the oil or liquid presence in the liquid tank. And yeah, apart from that, you can actually detect the sludge as well, similar to the one which I showed earlier. So you can detect the sludge which is present inside the tank, these kind of slags in the tanks. And apart from that, if you have a detection corrosion which is happening in the tank, that can also be detected using thermography in a passive manner. So here again on energy inspection on way, this was Tata Steel. So this is actually an iron mixer heating furnace. You can see there is a refractory lining losses here. So, but if you look at the thermal visible image, you are not able to detect anything, whereas the thermal image is clearly showing you the refractory lining losses. Similarly, in the blast furnace, again refractory lining losses could be detected. This is again deposition in the pipelines of the same Tata Steel, that could be clearly seen in the blast furnace gas pipes. And some of the other applications are in the field of building, where this is extensively used for quality control of the evaluation of the building, or for the finding out solution for the existing building. There are a building where they have a problem of entrapment of moisture inside the building. So those kind of things can also be solved using thermography. I'll give you one such example for that as well. And of course, quality control evaluation using thermography can also be done. Mainly in cold countries, they use extensively this technique for thermal envelope inspections. Complete building envelope inspection is done, and ventilating condition systems, how the conductive heat losses happens through the wall, interior finish, everything is studied. Without a thermographic certificate, you cannot sell or buy a house in most of these cold countries. So for thermal envelope inspection, this is extensively used. Similarly, structural inspection buildings, for the quality of the structure, thermal integrity of the masonry structures, this is extensively used. So these are some of the examples of the energy audits. You can see that in the gaps of the doors, there is loss of heat. That again, these are all mostly in the cold countries, so they keep their houses warm using the heater. So they don't want any kind of heat losses through these kind of doors or ventilation system, your windows. So similarly is one such heat losses through this one. And here is the moisture entrapment inside a building. Here you can see that this appears as a cold spot, okay, when it is appearing inside a building. Whereas this is because of a moisture entrapment. How this moisture entrapment took place in this 150-year-old building was, there was a crack here at the top of the roof where water was ingressing inside and getting accumulated in this area. This is one of the old church, where you can actually see the missing paints in all the areas. I think it's one of the Italian churches where they have used thermography for these kind of applications. Similarly, this is used for finding out the buried pipelines. Actually, these are the tiles under which this kind of hot buried pipelines goes on. Again, in a cold countries, you can see there is some kind of leakage which is happening. So that could be clearly detected using thermography. Similarly, industrial unit poor insulation. That is similar to our process industry insulation losses, which I discussed earlier. So such kind of insulation losses can be detected. Similarly, in delamination in concrete could be clearly seen. These are two hotspots which is seen in a concrete structure just because of the delamination which is present. Again, heat losses in the complete building. And here the timber frame, this one has been clearly detected using thermography. Here is the one which I was talking. Inside the building, I could see as a low temperature. when the moisture gets trapped. The same thing when it is there in the top of the roof and when it is exposed to sunlight, again thermal capacitance come into picture. So here it will appear as a hot spot. So you should understand in which environment and what you are inspecting. So somewhere it will appear as a cold spot, somewhere it will appear as a hot spot. So this is one clear example of that, where actually moisture saturation is happening, but because of the exposure to sun for the whole day and night, if you do the inspection, because of the higher thermal capacitance of water, moisture present here, you will be visualizing a hot spot, whereas the same thing inside a building you will be visualizing as a cold spot. So similarly for roof of the heated interior is mapped here, and building showing the effect of air filtration. You can see that these are all the effect of air filtration, and here is the one insulation loss in one of the building. You can see a hot spot here. So similarly, as Sir told, this can be used in the aviation industry extensively, particularly in the aerospace industry. They have a very peculiar problem of water ingress inside the composites. The water goes inside the composite, and when they go to the very high altitudes, what happens? Temperature falls down and the water gets frozen. That means it go from liquid state to it goes to solid state. Then that causes pressure to the stress to the nearby components, nearby composite panels which is present. So because of which you will have defects which will be formed later. So immediately after an aircraft landed, this is purely passive. They keep a series of cameras and try to see what are the thermal signatures which is recorded, and as rightly said, they try to identify the areas of, localize the areas of which need to be inspected further, and then try to do the inspections on the required region. Similarly, they have done on, so you can see that for a large structures, within few seconds they are able to inspect and tell what is the problem and isolate and do the further examination. Similarly, in the propeller side of an aircraft, you can see a very large thermal abnormality which is present, which was taken up immediately. You can see this is, they have actually done the threshold and removed all other just to understand how it goes on, and then they were doing the investigation. Similarly, in any automotive industry, for studying their airbag, their springs which is present in the seat, and of course the heater which is happening, of course for tire inspection, to understand the wear and tear of the tire and the heater, this is extensively used in automotive industry. Coming to the mechanical systems, yes, as I said before, this is used extensively for understanding the problems in the mechanical systems, because most of the mechanical system create temperature, and if there is any problem, there will be a change in temperature which they can record. This is again misalignment of the pipe. Here you can see there are a lot of rust which is formed, and it is causing overheating on that region. Deposition is there. Once the deposition was removed and properly oiled, this temperature raise came down. And similarly for any pump, overheated pump, lubricant deterioration, that could be clearly detected. Because of lack of lubrication, there was a hot spot which was detected. So that could be clearly brought out here. Again, storage tank, which shows clearly the level of in the storage tank. Similarly, this can be used for leak detection. This can be used for any kind of gas leak detection. Again, we should be very careful. There are gases which are completely transmitted, which can 100% transmit IR radiation. It is not for those gases, but there are gases which can be blocked by infrared and you can image them. Those kind of gas leaks can be detected clearly. Here is a one case where the steam trap, one of the steam trap was not working properly. That could be clearly detected. Here, I don't know whether you are able to get the contrast. You are able to see some black kind of region here. That is the leak. So this is the picture of photographic of it, whereas this is the IR picture of it. You can see a black kind of cloud kind of thing. That is actually the gas which is leaked. So that could be clearly detected using IR. Similarly, this is a seal joint in a gas turbines, in a steam boiler. This is a photograph of it, whereas this is an IR image of it. You can see there is a leak here. You can see a black contrast or gray contrast here. So that is because of the leak which is present. So apart from the regular, this kind of leak detection can also be done using thermography. Okay, these are again Sharath has already told, so I'll not go into the details of it. So one thing which I'll touch it in a little bit other manner so that it is complementary to you. So you actually this person is wearing this watch for a very long time. We all know that when two components at different temperature are in contact forever, they will get thermal equilibrated at one point time. But still, after wearing for a very long time also, this is appearing cooler, whereas the hand is appearing hotter. That is because this is a metal strip which is having a high reflectivity. So because of which you are seeing this as a lower temperature compared to the higher temperature. So this is the major issue when you are talking about passive thermography. There is an emissivity difference because of which it is actually appearing. But because since both are there in almost equilibrated, it should appear actually at same temperature. But because of the emissivity difference, it is appearing as if it is at a lower temperature and this is at a higher temperature. So you should be very, very careful when you are doing the inspection and in these kind of things. You should be doing your emissivity evaluation clearly before going into. Some of the things are already there in the literature which you can take. Otherwise, you do a simple experiment on your field like sticking the black tape or coating a black paint of known emissivity and trying to detect your own emissivity of the component and then try to do your estimation. So next one which they were all talking is the atmospheric transmission path. So when you take the transmittance percentage along with the wavelength, you will see that this 3 to 6 micron wavelength, you get lot of gaps between each of them. Whereas for 8 to 14, you get a very, very constant. That's why they tell that for larger distances, long wavelength is better because you don't see that much variation in the, but still your transmittance will be lesser than what you are seeing in your 3 to 6. But overall, the from a wavelength of 8 to 14, you will have above 80% of transmission. So that's why they prefer this. And the main problem of this is there are water molecules and carbon dioxide molecules which is present in between your imager and your object. So that means these are going to absorb infrared radiations. So that means there will be a loss of my signals. So I need to do the appropriate correction for this. That's why we need to measure what is its relative humidity, what is its ambient temperature. To be more exactly, you need to tell the camera that this is the ambient temperature, this is the reference temperature, and this is your amount of moisture which is present inside the measurement what you are doing, and this is the minimum distance. So then only it will be able to differentiate and understand that no, my camera, particularly when one of the application which I was talking is the mapping of the skin temperature of the cracker unit, where the cracker is at a different temperature, the flue gas is at a different temperature, and I am doing the whole measurement from a peephole. Okay, my camera is actually at 30 degrees Celsius or 40 degrees Celsius, but my object is at a different temperature. So I need to tell the camera that your ambient and reference temperature are different for your case. So those kind of understanding has to be there when you're doing inspection for using thermography, particularly for passive thermography, for when you are trying to measure the actual temperature. So this is one such example where you are seeing it appears nicely as in hotspots. In the again transform in a, I think it is I think Tarapur, it's an insulator only, ceramic insulators, which is again showing very nicely a couple of hot spots here. When you just take the picture and try to evaluate, then you will end up saying that this is a hot spot. But if you actually look it very carefully, if you are suspecting any kind of hotspot, whether it's a true hotspot or whether it is a reflection, because what you need to do is very, very simple. You need to change the angle of the reflection. As rightly said by CVK sir, when it is a reflection because of these solar, it will change, you will not get it at all the places. If it is a hot spot, true hotspot, then it will appear at different angles as well. So when you're doing the inspection, when you're finding out any hotspot, please try to map it at different angles as well, so that you ensure that it is the actual hotspot and not a furious reflection which you are picking up from some other component. The images may appear easy to interpret, but actually quantitative evaluation, you need to understand good amount of object which you are characterizing. Of course, definitely the infrared physics of it. And you can use any of the trending techniques or condition monitoring and processing models for excellent versatile, use thermography as an excellent, versatile and indispensable tool. With this, my first presentation is getting over. If you have any specific, this one, let us add. Apart from this, if somebody is there from this one, you can also do corrosion under insulation also using thermography in passive thermography, where you again the moisture absorbs the sunlight the whole day, and you do the inspection in the night. Because of the variation in thermal capacitance, you will be able to detect the corrosion under the insulation as well, and the moisture presence in the insulated component.
Ma'am, hello. Ma'am, we have seen the area of application which is directly contact to the IR. But it is also applicable which is a heterogeneous medium, like there is some concrete slab and in between there is TMT bar. And I'm talking regarding about the tunnel which is under water line like metro or other medium. But there is two atmosphere. One is heterogeneous, there is crossing the metro line, and which is another is the directly colder water. Then during this energy is reducing continuously, and some cracks occur in TMT bar and suddenly collapse it.
Okay.
So my area is concerned only that it is applicable also, which is there under some concrete.
What is the concrete thickness, sir?
Suppose 300, 500.
So then it cannot penetrate that much. I'll show you in the second this one. But there again we have done up to, it will not be up to 500 mm or something like that. So it is for a concrete of very low thicknesses where we have found the reinforcement bar corrosion which is happening. But that is over which concrete of very low thicknesses, not for this high thicknesses. Definitely here it has to, as I said before, my delta T, the temperature difference should manifest at the surface, and only I'll be able to create. I'll be able to image. As rightly said by Ravi Babu sir, if I give do an active thermography, give the heat input and try to, but there also it cannot indefinitely do for higher thicknesses and so on. Because even in the steel, we do up to 3 mm or 4 mm in my steel. That is mainly for nuclear applications. In aluminum, you can go for a higher, and composite, you can go for a little bit higher, but not to such a large extent you penetrate inside. And of course, if there is a leak which is happening, and because of the there is a contrast which you are getting, then you may be able to detect it in a buried pipeline kind of thing, but not in this case, I believe. We have done on corrosion reinforcement corrosion bars, which I'll be showing in the next this one, but that is not for the larger thicknesses of concrete.
That means this test medium is not limitation.
Yeah, yeah. Thickness is a limitation. This is not a technique where I can penetrate like in my radiography, as rightly said by sir. What I'm seeing, like my wavelength is, I'm imaging with an X-ray and I'm imaging with an electromagnetic. My wavelength is different, so I cannot penetrate inside and see what is there which is present. So there is a limitation on thickness. Definitely, there is a limitation on thickness. Okay. We cannot indefinitely find out everything under this.
Thank you.
Any other question? So, but I have a question.
Yes, sir.
You were talking about the cracker unit, and you were talking about the camera which was at some temperature and the cracking unit is at some temperature, and you have to tell the camera that the cracking unit is at different temperature. Is there any error involved if something like we have high temperature error in UT thickness measurement? Is there any error?
Here error will be there because I am trying to measure something in a non-contact manner, and I'm trying to give all these parameters like my emissivity, my distance, everything which I give has to be proper, so that I get a closer estimate of my skin temperature of my cracker tubes. Yes, there will be a percentage of error. I will not tell that it is not there, because I am assuming that the flue gas temperature is at by whatever the number which is set by my control room. Actually, it need not be there in the actual distribution. And for example, in the case of there were places where the burner were very close. They were turning the burners in here and there. So some crackers were seeing. So I had taken the readings of what the control room has told, that this is the temperature which is recorded by the thermocouple which is present there. So based upon that, we give. Why I told that was, for all other applications, we will be taking this ambient temperature and reflection temperature as one. Whereas when these kind of applications happen, you need to tell the camera that you are at a lower temperature, but what you're imaging is at a different temperature. So you need to understand that. So that for that only different temperatures, most of the time, like default people will tell ambient temperature 25, you keep that also 25. That happens in certain application, but when these kind of high temperature application happens, you need to tell the camera that you are at a different temperature and the object which is your viewing is at a different temperature.
Thank you. Any other questions? Nothing. So we will have a short tea break, and Menka madam will continue after the tea break again. Thank you very much, ma'am. Before we start, we would take a group picture first, okay, and so that one of the faculty wants to. So we'll have a group photo first. So I request all of you to come here.
Good evening to all. The last presentation of this session is on application of thermography for material characterization and evaluation. In this, I thought I'll be talking about a little bit different on online weld monitoring, which is also called as intelligent welding or feedback welding and so on. Thermography is one of the technique which can be used during welding process itself for finding out defects as well as for characterizing the weld parameters. So how we can detect defects during the welding process itself, because all the other entity like radiography or eddy current or ultrasonic all are done after the welding process is completed. Whereas thermography is one technique where you can use it during the welding process itself. That is, when the torch is actually moving like this, if you see that if there is a lack of penetration, which is nothing but an insulator, it will appear at a different temperature compared to the sound material. So then you will be clearly able to map the thermal signature of the defect. So similarly, I have a tungsten inclusion, tungsten is having a very high thermal conductivity compared to an stainless steel material. So again, this will show a different thermal signature compared to my sound material. Similarly, for sand inclusion or any kind of other defect which is present will create a different thermal picture which is unique for that defect will be created, which can be detected using during the welding process itself. So when the torch is moving ahead, you put a camera at the back and you monitor the weld pool temperature. For a good weld, you will have a something called as butterfly like structure. That is, you will get a very good symmetry between. If you draw a line like this, you will see a very good symmetry between it. So in that case, we call it as it's a very good weld. Otherwise, if there is an asymmetry in the thermal pattern, we call that this is a there is some kind of defects which is present inside the weld. So during the welding process itself, the defects can be detected. Apart from defect detection, I told welding parameters can be characterized. How do I do that? As I said before, when the torch is moving like this, you just monitor the weld pool temperature. When you just draw a line profile across this weld pool, you will get a curve like this, which we assume that it's not exactly Gaussian, but you can assume it to be very close to Gaussian. You can see there are two areas where you call it as point of inflection. These two areas, which we call it as point of inflection, that's where your liquid solid interface lies. So that means that the distance between these 2 points of inflection where my liquid solid interface lies will give me my bead width. The area under the curve will give me the thermal input. That means I can, by monitoring a welding process online using an IR camera, I will be able to tell whether thermal input is directly proportional to the depth of penetration in a welding. So that means what is the depth of penetration I can tell, what is the bead width I can tell. So that means indirectly I am characterizing my weld completely using thermography apart from detecting defects in the online. So these are the isothermal patterns for different depth of penetration. That means this is something around 60%, 80%, 100% penetration. If I just draw the curves for all these things, you will get like this. So you can see the area under the curve for 60%, 80% and 100% is different. For 100% it is higher. That means my thermal input is higher, my depth of penetration is higher. So thermography, apart from these kind of condition monitoring, can be used as an tool for these kind of process monitoring as well, online monitoring as well. So here again, it is a passive imaging. I am not giving any kind of heat input. The welding process itself is giving me sufficient delta T, which is creating me this thermal signatures. Similarly, this we have used for inspection of our end plugs to the fuel pin. This is fabricated in our NFC Hyderabad. So for inspection of these end plugs, such kind of end plugs for the fuel pin, we have used thermography and we have got very good correlation with metallography. Apart from that, the new trend is now is hybrid welding, where they combine laser and TIG welding for welding processes. That is just to ensure that if you see, look at here, that if you are using a laser, my bead width will get reduced significantly. That means, and my depth of penetration will be higher. So now people are going for this kind of hybrid welding. Again, here we could use this technique clearly for identifying the different penetrations in that and what is its bead width. This is again on the same thing. This is on stainless steel 316 LNs where we have done the hybrid laser welding. This is one of our nuclear applications. You can see the depth of penetration in y-axis and the microscopic temperature gradient in the pixel in this. You can see that the for higher 100% this one, that the depth of penetration is very higher temperature gradient. You can see the This one depth of penetration was almost 100%. Similarly, the thermal width or bead width, that is the bead width is the weld bead width, and this is thermal width which we get it from the thermograms. So that we found that it is linear. Similarly, the weld from the weld center line, how the heat affected zones temperature is, what is the temperature which is raised by the heat affected zones, and how will be their microstructure which will be varying, that was analyzed. And here we got the temperature at different points at the weld at the different distances, that also has been mapped here. So this is one work which we did for our fusion reactors. These are tungsten tiles and copper tungsten tiles which is brazed to copper block. So how good is the brazing was detected using thermography. Here it is active thermography. I am not talking about passive here. So here it is active thermography. Here there are a couple of standards which is referred by the Japanese, particularly they called this hot cold simulation, which they use extensively for IPR, tokamak components. So this hot cold simulation is nothing but they send hot or cold fluids through this pipe and try to find how good is the brazing. The same thing is done through induction heating as well. This is a round robin test in which we were also a part of it. We tried both using pulsed and lock-in. We could see in lock-in, we could clearly find the degraded and the level of degradation variation as well compared to the one which is there in the hot cold simulation and pulsed. So another one interesting application of thermography is we have clubbed here our HLT, helium leak testing, vacuum technique and thermography. This is for finding out, you can see this is a complex structure which is a part of our reprocessing plant. So you can see that these are failed joints, some of the failed joints for which first they wanted to carry out a helium leak tester to see its leak tightness, but they could not create sufficient vacuum inside the component because there was a gross leak. So what they did was they thought that they have to go for a radiograph of this. You can see that there are a lot of joints here. So each joint X, Y, Z, it will take a number of the time required for inspection would be higher. So what we did was we just thought of a small work, and then because it was not holding the vacuum, what we did was we using our IR camera, we tried to image that component. Wherever there was a failed joint, there was a cooling effect. This is called Thomson's cooling effect. That is, when a gas is passed through a small hole, when suddenly it expands, cooling effect will happen. So because of which we could clearly detect the failed joints in this one just by doing an IR image of it. So, but what here is most important, here you cannot call it as a passive. As sir was discussing, there are various methods of inducing the temperature difference. This is one such method where we were trying to generate a vacuum inside the material, but because of the gas passing through it, the low temperature was detected. So that created this contrast. So this is one such, this one. Similarly, there was one bellow assembly of, which is used in one of our reactors. So that assembly had some kind of problem. So we could, actually there was a leak. You can see there is a drop in temperature here. We again detected it very clearly in this bellow, but whereas this is another bellow where there was no leak. So apart from that, this can be used for coating characterization. When you talk about coating characterization, this can be used for metal to metal coating characterization or thermal barrier coatings as well. This thermal barrier coatings is for our reprocessing side particularly, where we are looking for a thermal barrier coating, where EDDY coated on thermal barrier coatings we were studying. So again here clearly we could differentiate between the reference HDG and the EDDY silica coated base substrate and the delaminated one. Again using lock-in and pulsed, we have clearly detected using that and we have characterized it. This is on metal to metal, whereas this is a thermal barrier coating. This is a metal to metal coating. This is 5 micron, 10 micron of nickel boron coating on a stainless steel plate. This is again for our reprocessing site. This is for our corrosion purposes. To avoid corrosion, we coat the stainless steel, this one with a nickel boron coating. So there you can see that delaminations, the disbonds between the nickel boron coating on the stainless steel plates were clearly detected. And you can see that there is a variation in the color between them also. This is also a delamination, this is also delamination. So the level of gap which was present between them was also varying, which is causing a temperature contrast here as well. So that also, this is a C-scan image of taken using an UT immersion system. You can see that this is giving a better spatial resolution compared to my UT immersion. Of course, we did both pulsed and lock-in for characterization of this microcoating. Okay, this is one. Okay, this is one of the component of our reactor, prototype fast breeder reactor, which we call as grid plate, which is connected to the core support structure, and this is a sodium pump. So these, and this is again CSRDM, these are some of the components for which we need to do hard phasing alloys. Hard phasing deposition has to be done. So hard phasing deposition means there are two problems which two things we would like to characterize in that. One is detection of disbonds or which is present between the columnoid layer and the stainless steel, or it can be the thickness variation. So both could be detected using thermography, again using active thermography. That's what I'm showing here. So for a 3 mm and 2 mm, you are seeing the contrast here. And similarly, a disbond which is present in the columnoid coating on a stainless steel substrate could be clearly detected using lock-in thermography. That has been detected here. Similarly, if you look at the literature, a lot of study would have been done on composites, because thermography is extensively used for composite characterization and evaluation. But for stainless steels, there have been minimum amount of work which has been done, because one interesting challenge which you have here is, because of thermal diffusivity is higher, it is little bit challenging finding out defects in these kind of highly thermally diffusive material. So we arrived at different, we studied we made our own samples, calibration samples, and we studied this both with pulsed, lock-in, and what is the sensitivity to detect the defects at different one, and different processing methods, as rightly talked about by the previous speaker. Different processing methods which will enhance my detection and contrast. So similarly, we used this technique for concrete evaluation as well. We have structures, concrete structures, which would be facing sea. That means some of our structures face the seawater. So they have a challenging problem of biofilm formation. What happens is, these biofilms which forms on the surface releases sulfur, and they actually causes deterioration of these concretes. So they wanted to map the morphological mapping of these biofilm formation, and how much there are different composition which has been used to show the resistance of the biofilm formation on this concrete. Some is the the first one is actually the normal concrete, the second row is actually fly ash added, again the last one is the superplastizer. So we found that the fly ash and superplastizer showed a good resistance to the biofilm formation. So that could be clearly detected using thermography. So this is the one which I was talking about. Here actually we had two reinforcement bars. What is the thickness, Sharath? You remember what is the thickness of the? I believe it is 25 mm, sir. This is 25 mm. So this actually, one is a corroded bar, another is a non-corroded bar. You can see that using lock-in, you are able to see this rod alone. This rod you are not able to see because the rod has moved inside, and because you are seeing the crack, no sir, this has gone inside and the crack has, spallation has started happening. So that's why this displacement has got, because actually both are at the same depth, because this corrosion has accelerated and this has displaced from the place. So the same as what said by Professor Ravi Babu sir, the wavelength means that it diffuses to that particular thermal diffusion length. It has moved from that place. That's why you are not able to image the other rod, but the defect which is formed because of the spallation has been detected here. So for these kind of this one we can do, but for a very high thicknesses we have never tried. This is for one of our application we tried it. Similarly, for this is again for our nuclear industry. We use high density concretes for our certain shielding, biological shielding purposes, where we use steel balls of 3 mm and 4 mm. When you use steel balls on a concrete, what will happen when you are doing curing or something, because of the density, it will come down, come and settle down. But we don't want that. We want a uniform distribution of these kind of steel balls in the this one. That uniform distribution of these steel balls, we try to do it using thermography. You can see that all these small this one, or all these steel balls which is embedded on that, and we did that for different directions, and we could see actually the map the different distribution surfaces of the steel balls on the concrete. Similarly, these are all on-field applications which I'm talking about right now. This is actually a 550 NB elbow pipeline which comes on the secondary side of our sodium pump, the sodium side of our prototype fast breeder reactor. This was subjected to cyclic loading. There was a notch which was generated, and we wanted to find out, completely characterize the crack which is formed from the notch. So what happened is, when we did lock-in thermography of it, these are the halogen lamps, you can see that, and this is a camera. There was a notch here. So you can see this is the thermal image of it, actually phase image of it. You can see this is the notch, this is the crack. From there, this crack has branched out, and this is another crack which is going downward. So apart from this, exactly at the opposite side, there was a natural crack which has appeared, and the crack, we actually characterize the crack length and depth of it using thermography clearly in this component. So you can use this extensively for these kind of application. This is one such application where we have used this thermography for understanding the heat transfer which was happening within the system. That is particularly, this is a periscope assembly, lamp assembly. I believe it is a long, 10-meter long. This periscope assembly is for our prototype fast breeder reactor. So this is going to come here. So this is a 10-meter long component. Here actually they were placing this periscope lamp. This was tripping very frequently because of the overheating. So they wanted to understand how the heat transfer is there, whether the argon supply which is given to it should be improved, or how we have to change any other purging gases or things like that, how the cooling effect is happening. So we studied that extensively and we modeled it. So we could clearly tell that what should be the LPM, and whether this gas gives a better cooling effect or not. So such kind of heat transfer things can also be understood and implemented for putting a better system into a component or process. So this is again, we can do failure analysis also using thermography. This is one of the neutronic instrumentation side of our Kamini. Kamini is Kalpakam mini reactor, which is a reactor which is running in uranium-233. That is, thorium is converted into uranium-233, and it runs in that. Very few grams of uranium-233 we have put long back, and still it is running. It's a very compact reactor which is just half of this place. So we switch it on and switch it off just like how you do for your fans and AC. So here this was extensively used for neutron radiography. So the neutronic instrumentation of this Kamini reactor got failed. The frequent tripping was again happening for them. So what we did was to identify, as we know that if it's a neutronic instrumentation, there will be too many components. We first wanted to know what is causing the overheating or the problem. So first we energized it and we found that there was a local heating, and then we did lock-in thermography. We found there is a dielectric damage which is happening, because of which you are seeing a rise in temperature. So this we could clearly detect using thermography. This is one interesting phenomena which happens in our reactor. It is called thermal ratcheting because of the variation in the temperature. our vessels are all very small, very low thicknesses, that is around 2 mm, 3 mm thicknesses, this particularly for our PFBR. So when these are subjected to the thermal ratcheting, the different thermal gradient because of the sodium movement, because of the shutdown and then again starting. So that thermal ratcheting phenomena of the which would happen on the vessel has to be studied. For that, thermography has been used extensively, and that input has been given to the modeling, and then we could clearly find out how much of deformation will happen in the vessel because of the thermal ratcheting. So this is one study which we have done for tensile deformation. When you are subjecting any material to deformation, particularly tensile deformation, 80% of the work which is done on the material is converted into heat, 20% into acoustic emission and some other energy. By monitoring this amount of heat emitted by the object, you will be able to tell where exactly it is going to fail and how the rupture is going to happen. So that's how we used this technique, IR imaging, for characterization of the tensile deformation. That is, you can see that during the temperature versus nominal strain, as the strain increases, slowly the temperature increases. There is a small dip here, that is because of the thermoelastic effect which was happening here, and you can see that the temperature at the region of where it is going to fail was continuously increasing. Okay. So you can see that at 7.1% the temperature was lesser, whereas at 60% where it is going to fail, it was continuously increasing. If I draw a line profile, you will get something like this. You can see that at the where it is getting ruptured, the maximum temperature was always there. That means the stress concentration in that area was always higher where it is going to fail. So you can, by using this, I can actually predict my zone of failure. That means I can tell somewhere at less than of 10% of nominal strain itself that this is where it is going to fail. So that is very, very important, this one, for any component which is under static load or any kind of load. So this same thing we used it for MLP, AI based this one, to predict the strain and stress. And this is another study which we did for sodium fire studies. That is, we use sodium as a coolant for our reactors. Sodium is very reactive both in air and water. So sodium fire, in case, because we handle tons and tons of sodium, if it gets fired up, then how its behavior will be there. We need to understand that. So what we did initially was we took sodium and petrol, and we studied the difference between the petrol. This is a petrol fire. This is a sodium fire. You can see that the flame length of a petrol fire will be higher, and whereas here it was very much confined. The flame length was not that much and very much confined. So you can see that this goes maximum, and then we intentionally decreased it, whereas this goes, but still it was confined to the vessel itself. And similarly, we did this sodium fire study inside a quartz tube, and then we mapped this one using IR camera, and how the temperature varied, how the aerosol formation was there. All these things were studied using thermography. So this can be used for studying fire characteristics as well. Similarly, cable fire studies, I believe some of you might have heard also in one of our reactor, NPCL reactors, there was one cable fire which took place starting from the turbine side. It actually went up to control room side. So we were asked to study this cable fire, how the cable fire is generated, and how the transmission happens through the cable fire. So for that, again, thermography was used, different cables, how and what is the, they were using some sheath like this yeah, fire resistant cable insulators. So if you use that, then how is the cable fire is not happening that aggressively as when it is not used. So those things were all studied and given as a safety report for our regulator. Thank you. This is what I wanted to share. If you have any other, this one. Yes. Pardon, sir?
Well,
Regulation of, what is it asking? Standard for?
standard for evolution of thermograph.
Standard for thermography, I'm imaging of thermography.
Yes, yes.
Sir, BIS has a standard for electrical, this one, and ISO standards are all there for thermography, sir. For electrical inspection, for composite, it is there. General vocabulary, terminology, there are standards which is available, sir.
Madam, please explain corrosion under insulation, how we inspect with
Sir,
thermo.
again, corrosion under inspection, the same process. Water goes inside your insulator. So, if it is outdoor, like if it is seeing the sun, then during the daytime, this water stores the heat energy. And if you do the inspection in the night or evening time, generally this inspection, okay, outdoor inspection, I forgot to tell you. Generally, outdoor inspection is done 1 hour after the sunset or 1 hour before the sunrise. This is just to avoid the solar spurious reflections. So generally, when you do this kind of inspection in the evening, what will happen is that stored energy will be emitted in the night. So with that, we can actually measure presence of moisture there. If that presence of moisture has started corroding the your this one, then that will create different temperature value. So you will be able to clearly detect it.
Okay,
I have not shown the images. Sorry, forgot to add it.
Madam, Thomson effect happens for all gases or only for inert gases?
No, no, sir. It is not for all gases.
Only
It is
for inert
definitely
gases.
not for all gases. It is not.
For which gases? We now showing for medium liquid things.
Air it happens.
Only
Air
air.
it happens. It actually, this drop in temperature will vary with for argon, helium, everything. The drop in temperature will also vary. For some, it will drop very drastically. For some, it will not very drastically. For air itself, you will be able to see some amount of drop in temperature. But apart from that, helium is used. Argon is also in some of the cases they use.
Okay, thank you.
Thank you, ma'am, for your lecture. Can we replace the radiography by thermography?
No, no, sir.
Up to
You
what
cannot
extent?
replace. Here it is not. Each one has its own advantage.
Exactly.
We wanted to reduce the like, but still you need to confirm it because you and we IR doesn't have a standard
Exactly.
this one. So, but for reducing, at least you know that these are the ones which I need to. Even if you are doing your radiography, you will be very careful with these joints. Like
What I am
just to
asking to reduce to increase the productivity. Actually, I am
yeah,
thinking-
actually, you can do it, but yeah, if you ask me whether you have an ASME section 5 or 4, then you don't have, right? But you have standards for thermography, for electrical installation, and for other this one, and both in ISO and this. But for if you ask, I mean, actually, for example, in our this one, they will ask whether it goes by ASME section
Yeah.
5, section 8, and
Yeah.
so that we don't have. But yes, we do. What is the this one is our management do take our input, like certain things is R&D based. So this gets this helps the things to be done at a faster rate. So they encourage us in that way. But if you are asking your customer or somebody is asking you which standard, then it is that. So this will help you out in solving. That's why I showed one of the applications.
Thank you.
So, any other questions? Yes. Do you have? प्रश्न आहेत का? प्रश्न आहे का? आहे.
Ma'am, which IR source is used during welding? No.
Going on, when welding process is going on, the weld pool temperature will be 1500 or 2000 degrees Celsius, right?
Yes.
Not the torch. I will not concentrate on the torch. If my camera sees the torch, it will get saturated. So it's torch temperature will be 3000 to 4000. I will not go to that. My interest is weld pool only. That's why I focus my camera only to the weld pool, so that to find out here I don't use any IR source, sir. That's what I told. The process itself is giving me sufficient delta T. Why I need to go for an stimulus there?
During continuous process means welding is continuing and
Yeah,
we can
that's what
also
the camera goes. If you're depositing like this and going on, your camera moves on like this. If you're doing circular welding, then it goes like this.
Ma'am, as you said that in painting,
Hmm.
after applying the painting after 7 days or 5 days, if we examine, then we can find out the crack also. But during production of painting,
Hmm.
can it apply?
I
Can,
have
there
not.
is organic material or inorganic material to identify or distinguish between them.
No, I don't think so. There is, there is no.
Thank you, ma'am.
Any more questions? I think no. So thank you very much, Milka ma'am. So now we have practical demonstrations. So nobody should leave this, and it may take another half an hour or 45 minutes, not more than that. So please wait here. There will be two demonstrations, one by Injo Technical and one by KB Quality Services. Okay. So please wait.
Okay.
त्याला 3 पॉइंट नाहीत रे. हॉटस्पॉट आणि कोल्ड शॉट आहे ना, ते पण घेऊन दाखवा मध्ये ऑटो. चार्जिंग किती बघा, मध्येच बंद होतं अचानक ती. फुल आहे.
तो काचर करायचा इथं झूम करून दाखवायचं असं. Ready? Hello everyone. We are from Injotech India Private Limited. Today we introducing portable thermography device. This is a Fairmec E60. So currently I just on it and focus the lens as per your distance and just click it. After taking images, there are two images saved, like एक thermal images and regular camera images, like this. This is thermal image and this is regular camera image. There is a camera from outside of the lens. This is the camera and there is a arrangement of laser like this, which area we want to inspect. So it's guide us which area want to take. So their function is in setting measurement parameters can set like humidity, reflective temperature, distance, relative humidity, atmosphere temperature, save option, preview image before saving, add another after saving, like this. And second is measurement. Now current measurement is center point, means here is the center cursor. It shows the center temperature like 26, 27. Now I am changing hotspot. Hotspot means in this window, like white window appears, we can adjust it like scroll, drag it, and in that area it shows maximum highest hot point. like this. It is varying now. Now it is stable. So then we can detect highest hotspot. Same like this. Another measurement method is cold spot. Same like this, we can adjust window and check. Now it shows hotspot of maximum hotspot. Sorry, cold spot. Third one is 3 spots. Like 1, 2, 3. It shows area of uh, 1, 2, 3. 3 spots temperature it shows. So use this measurement method as per your requirement. Fourth one is average it, hotspot and spot. It's average like a center point and hotspot. It shows maximum and spot and average difference between these 2 spots. Then there are device setting, setup camera. Camera temperature range is given. So currently selected is -20 to 120. In this model, there are 2 ranges, 0 to 650 and -20 to 120. So select before inspection as per your requirement. That's it. Any questions? Okay.
I mean, it's a government approval.
So, thank you very much. These were the practical demonstrations. The idea really was to go outside and see some solar panels. But then I thought this hotel is having those, but I was wrong there. They don't have any solar panels there, so that we can fly the drone and show how things look like. But then, since we had some, images and videos, we were able to show you everything. So if there are any questions, we are there always. So I say that this particular program gets completed now. So thank you very much for your attendance, and I would really thank Menka Madam, then Sharat, even Ravi Babu, and C.V. Krishnamurthy for giving very good lectures here. I would also like to thank all those who are here. They have supported us a lot. Injo Technical India Private Limited. They were they were our principal or platinum sponsor. Then Fabtech, we have they were our gold sponsor, and Foster's were our silver sponsor. So we thank them all, and I think we conclude with this. And thank you very much. See you for the next workshop. Yatin आणि ह्यांना दिला आहे ना काल